Hello fellow sapiens, and welcome to Sleepless Homo. Take a moment to breathe, quiet your mind, and let this slow storytelling keep you company, whether you're winding down for sleep or simply finding calm while working, driving, cooking, showering, or with headphones on. If you appreciate this kind of long-form, fact-driven science, humble science that admits we don't have all the answers, but does its best, please consider liking and subscribing. It helps more people discover thoughtful, educational content and, in its own way, conquer the world with knowledge. I'd also love to know how you use these stories. Before bed, while working, or even where you watch from. Share it if you'd like. This channel grows through curious sapiens like you, and if you drift off mid-episode, don't worry. I've placed timestamps in the description so you can pick up right where you left off, because every chapter of this story is worth hearing, and as always, stay curious, stay calm. Tonight's story begins billions of years ago when oxygen, the gas that makes us possible, almost ended everything. What would it be like to live on a planet with green oceans and no oxygen to breathe? The Earth of 3 billion years ago would not have looked familiar to us in any way. The continents as we know them today had not yet assembled, and what land did exist may have amounted to only a scattering of volcanic islands and a few larger fragments pushing up above the waves. The rest of the world was covered in water, a water that was not blue but green, tinted by dissolved iron and chemical reactions that painted the seas in hues we would now call alien. Above those seas hung an atmosphere dense with nitrogen and carbon dioxide, streaked with methane that gave the skies a hazy cast. Oxygen, the gas we consider essential, was almost absent. If you or I could step out onto that shoreline, our lungs would find nothing to pull from the air. The very chemistry of the planet was hostile to our biology. And yet, life was already here. The world was dominated by microbes, though not the kinds we might think of today. These were anaerobes, organisms that could not only survive without oxygen, but for whom oxygen would have been a poison. They harvested energy from chemical gradients at the edges of volcanic vents, from the interaction of hot water with minerals in the crust, or from the breakdown of methane and other gases. Their metabolisms were unfamiliar, running on electron transfers involving iron, sulfur, and hydrogen. The seafloor in particular was a crowded neighbourhood, black chimneys of hydrothermal systems belching minerals into the water, microbes clustering around them in dense mats. To these cells, the shimmering mix of metals and reduced compounds was food, and they built their existence on it. If we try to imagine Earth as an alien world, this is perhaps the best example we have. An ocean planet suffused with gases that would choke us, alive with invisible chemistries. At the surface of the oceans, the colour of the water was dictated by a peculiar form of rust. Today, we're used to rust being red-brown, iron oxide forming on abandoned metal. But under low oxygen conditions, iron chemistry can take on a different cast, producing what is known as green rust, a layered iron hydroxide mineral that forms when iron is dissolved in seawater rich in chlorides and sulfides. The oceans of the Archean Eon were saturated with iron, poured into the basins by constant volcanic eruptions and hydrothermal inputs. In the absence of oxygen, it stayed dissolved, circulating freely through the seas. The world was, in that sense, a giant solution of metals, waiting for any disturbance. To us it would have appeared as a strange green shimmer extending from horizon to horizon, reflecting a sky of muted tones. The atmosphere above those seas was equally strange. It was mostly nitrogen, as it still is today, but with a far higher contribution from carbon dioxide and methane. Methane in particular would have been abundant, produced by archaea that thrived in anoxic conditions and belched this gas into the air. Methane is a powerful greenhouse agent, and so it trapped heat effectively, keeping the planet warm despite the sun being significantly dimmer than it is now. Astronomers estimate that the sun of 3 billion years ago was about 20% less luminous than it is today, meaning without methane and carbon dioxide, Earth might have been locked in ice. Instead, the blanket of gases made the world a greenhouse, warm enough for liquid oceans to cover its face. For all its strangeness, it was habitable, but only for microbes built to live without oxygen. What is most remarkable about this time is that Earth was stable in this state for hundreds of millions of years. Life, primitive as it was, had carved out niches and adapted to the chemistry available. Some organisms reduced sulfur, others processed hydrogen, others found ways to interact with iron. Energy came not from sunlight as much as from geology itself. Volcanoes, vents, and chemical reactions in the crust provided the gradients that drove metabolisms. In this way, Earth was self-contained, a planet where the living world and the mineral world were entangled at the most intimate levels. If we stood at the edge of one of those islands and tried to breathe, we would collapse instantly. But to those early microbes, the airless conditions were not a limitation, but an advantage. They lived in an oxygen-free Eden, oblivious to the possibility that anything could change. It is humbling to think that they may have considered themselves, if we can even anthropomorphize such simple life, perfectly adapted to a permanent world. Yet history shows us that the only constant on Earth is change, and their stability was only temporary. What made this world possible was the absence of oxygen. Without free oxygen, iron remained soluble, methane could accumulate, and anaerobic metabolisms could thrive without interference. Oxygen is a highly reactive molecule, hungry for electrons, quick to oxidize metals and break down delicate biochemical machinery. At this time, there was none to speak of. Our planet was chemically reduced, full of unclaimed electrons, and its surface processes reflected that state. Rocks weathered differently, rivers carried different loads, and volcanic gases lingered longer in the air. From a geochemical perspective, Earth was young and restless, its crust still in the process of cooling and stabilizing. It is difficult to reconstruct exactly what the land looked like, because so little of it has survived. Rocks older than 3 billion years are rare, altered by metamorphism and tectonics. But those that remain show evidence of small continental fragments, the beginnings of cratons that would later assemble into supercontinents. These proto-continents would have been barren, lifeless surfaces of volcanic basalt and granite, perhaps dotted with microbial films at the edges. No plants, no soils, only naked rock exposed to rain and wind. The cycle of erosion and deposition was already active, but its participants were stones and water, not trees and roots. The seas were not only green from dissolved iron, but also likely turbid with particles, stirred by hydrothermal activity and constant inputs of minerals. They would have been rich in dissolved gases, including carbon dioxide and hydrogen sulfide, making them pungent and perhaps acidic. To us, it would have been a stinging environment. But to microbes, it was an endless buffet. Many archaea still alive today are considered extremophils because they thrive in hot springs or vent systems. But 3 billion years ago, these conditions were the norm, not the exception. Extremophils are, in that sense, survivors of an ancient way of life. One of the great mysteries of this time is how stable such an alien balance could be. With the sun dim, with oxygen absent, and with only microbes to drive the carbon cycle, Earth might seem precarious, but it held steady for long intervals. Some scientists suspect that methane feedback loops provided stability. As microbial methanogens produced methane, they warmed the planet, which increased weathering and limited further methane buildup. These negative feedbacks may have kept Earth from spiralling into permanent freeze or runaway greenhouse. It was a fragile but functional equilibrium. This picture is drawn from multiple lines of evidence. Ancient sediments preserve chemical signatures of anoxic conditions, detrital grains of pyrite and uraninite, minerals that would not survive transport in oxygen-rich waters. The absence of oxidized iron deposits before about 2.5 billion years ago is another clue. Carbon isotopes hint at microbial metabolisms, though interpreting them is challenging. Taken together, the record tells us that oxygen was absent and life was exclusively microbial. But the exact diversity of those microbes, their habitats and their interactions remain partly hidden. We work with fragments, trying to reconstruct a planet alien to our senses. For all the uncertainty, one thing is clear. If we try to imagine the earliest Earth that supported life, it would be utterly unlike our home today. We picture blue oceans, but they were green. We picture breathable air, but it was toxic. We picture continents crowded with life, but there were only sterile rocks and bacterial mats. The familiar world of animals, plants and skies with oxygen was inconceivably far away. Yet the seeds of that future were already present in the chemistry of the oceans and the inventive metabolisms of microbes. There is something quietly unsettling about this image. If life could thrive without oxygen for billions of years, what does that say about our dependence on it today? Was oxygen inevitable or an accident? And if it was an accident, does that mean life elsewhere in the universe might remain perpetually anaerobic, never making the leap we think of as progress? These are questions we cannot yet answer. We know only that our planet once looked very different, and that its inhabitants were content in a world that would now suffocate us. The story of 3 billion years ago is not one of dramatic catastrophes or towering creatures, but of chemistry shaping biology. It is a reminder that life is flexible, and that what seems hostile to us can be home to others. When we look back to that time, we are not seeing the prelude to humans or even animals, but a self-contained alien world that just happened to share our planet. It is humbling to remember that we are latecomers, dependent on a gas that was absent for most of Earth's history. Perhaps that is the haunting question to carry forward. Was oxygen always waiting in the wings, or did it nearly never come at all? How did microbes learn to turn sunlight into food, and why did that spell trouble? For hundreds of millions of years, life on Earth had relied on the chemistry of rocks, gases, and deep-sea vents. Energy came from gradients, from hydrogen mixing with carbon dioxide, from sulfur compounds bubbling out of the crust. It was a world where life clung tightly to the chemistry of the Earth itself. But between 2,700,000,000 and 2,500,000,000 years ago, a different way of living began to appear. Some microbes discovered that they could make use of the most constant and inexhaustible source of energy our planet had ever known, the light of the sun. The first experiments with light were modest. Certain bacteria evolved pigments, molecules capable of absorbing specific wavelengths of sunlight. To our eyes today, those pigments might have appeared purple, orange, or even brown. They were not the bright greens we associate with plants, but rather odd hues tuned to soak up the most available portions of the spectrum that filtered into shallow waters. These early photoactive microbes were likely what we now call purple sulfur bacteria and green sulfur bacteria. They did not yet use water in their reactions, and they did not release oxygen. Instead, they harnessed the energy of photons to drive chemical reactions, using hydrogen sulfide or ferrous iron as electron donors. The byproducts of their photosynthesis were not oxygen, but elemental sulfur or iron minerals. What mattered was not the specific waste, but the principle. These bacteria had decoupled life from its dependence on rare and localized chemical gradients. Instead of being limited to the immediate neighborhood of a hydrothermal vent or a mineral-rich seep, they could live wherever sunlight reached. In an ocean world with few continents and wide shallow seas, this was a game-changing expansion. Suddenly vast areas of coastline and surface waters were potential homes. Sunlight bathed every wave and ripple, and microbes had learned to eat it. Pigments were the key. Chlorophyll and related molecules are extraordinary in their ability to capture light energy and funnel it into biochemical machinery. In modern cyanobacteria and plants, chlorophyll absorbs red and blue light while reflecting green, which is why we see leaves as green. But in the ancient world, many pigments preceded chlorophyll's dominance. Retinol-like molecules, bacteriochlorophylls, and other compounds absorbed infrared or other narrow slices of the spectrum. To imagine the Archean seas during this transitional time is to imagine a water column tinted with the subtle colours of microbial blooms, layers of purple and orange bands drifting through the shallows. What these organisms gained from light was versatility. Chemical energy sources could be patchy and temporary, but sunlight was predictable. Each morning the star rose, and with it came a flood of energy that could be harvested. Once microbes mastered the art of capturing photons, they could grow faster, reproduce more often, and spread farther than those still bound to geochemistry alone. In evolutionary terms, this was a new frontier, yet the path to photosynthesis as we know it was not immediate. The earliest light harvesters still relied on exotic inputs. Green sulfur bacteria used hydrogen sulfide, producing sulfur globules as waste. Purple sulfur bacteria did the same, staining sediments with grains of elemental sulfur. Iron-oxidizing photoautotrophs used ferrous iron, producing ferric minerals that precipitated out in small quantities. These metabolisms were effective but limited, tied to particular environments where hydrogen sulfide or iron was abundant. True revolution came with the refinement of a simpler pathway, one that used water itself as the electron donor. At some point in this period, a group of microbes, ancestors of what we call cyanobacteria, evolved a photosynthetic system powerful enough to split water molecules. This was an audacious leap. Water is chemically stable, and breaking it apart requires enormous energy. But by linking two photosystems in sequence, cyanobacteria achieved it. They absorbed two photons in tandem, their pigments passing energy from one system to the next, until the force was sufficient to cleave water into protons, electrons, and molecular oxygen. The electrons went into driving carbon fixation, building sugars from carbon dioxide. The protons contributed to proton gradients, powering cellular energy production. The oxygen, however, was simply expelled. It is important to pause here because this innovation, water-splitting photosynthesis, is arguably the single most consequential metabolic invention in Earth's history. It freed photosynthesis from dependence on rare chemicals like hydrogen sulfide. Instead, it used the most abundant solvent on the planet. Oceans of water became fuel. With this, photosynthetic microbes could colonize nearly any sunlit environment, and the energy yield was high, allowing these organisms to grow rapidly and compete effectively. From a purely microbial perspective, this was a triumph of efficiency. Light became food, water became fuel, carbon dioxide became biomass. Stromatolites, layered structures formed by microbial mats, began to proliferate in shallow seas, recording the activity of these communities. Some stromatolites older than 3 billion years exist, but by 2.5 billion years ago they were widespread, suggesting that photosynthetic microbes had become ecological engineers, building layered reefs of cells and trapping sediments in sticky films. These formations, still visible in ancient rocks, are the oldest macroscopic fossils of life we can point to. The ecological consequences were immediate. While vent-dwelling microbes still thrived in the deep ocean, surface waters were increasingly dominated by phototrophs. This changed not only the availability of energy, but the cycling of carbon. Photosynthesis pulled carbon dioxide from the atmosphere and dissolved carbon from seawater, turning it into organic matter. Some of that matter was consumed, but much sank into sediments, altering global chemistry. Feedbacks between biology and the carbon cycle began to intensify. The story of these microbes is also a story of molecules. Pigments evolved under selective pressure to capture every scrap of usable light. Early pigments may have looked purple because they absorbed green and red wavelengths. Later innovations shifted absorption toward red and blue, giving chlorophyll its modern spectrum. In microbial mats, communities of different pigment users could even layer on top of each other, each exploiting the light left over from the layer above. This niche partitioning allowed diversity to flourish, with multiple forms of photosynthesis coexisting in a single environment. One might wonder how we know any of this. After all, we cannot peer directly into a world billions of years gone, but the rocks retain traces. Certain lipid molecules produced only by photosynthetic bacteria can persist for billions of years, preserved in sediments. Isotopic ratios of carbon hint at biological fractionation, characteristic of photosynthesis. Stromatolites provide morphological evidence. Together, these clues let us reconstruct the slow dawn of phototrophy. We do not have every detail, but the broad strokes are clear. Sometime around 2,700,000,000 to 2,500,000,000 years ago, microbes learned to use sunlight. What makes this narrative compelling is that photosynthesis was not inevitable. It required a precise sequence of molecular innovations, pigments tuned to particular wavelengths, proteins capable of transferring electrons, membranes to maintain gradients. That it happened at all is remarkable. That it happened relatively early in Earth's history, within the first 2 billion years, is even more striking. It suggests that life is inventive under pressure, always probing new sources of energy. For those microbes, the discovery of sunlight as food was an expansion of horizons beyond anything previously possible. Instead of clustering around chemical vents, they spread across entire shorelines. Instead of relying on rare minerals, they drew energy from the daily rhythm of dawn and dusk. The sun, which had always shone indifferently on Earth, was finally woven into the metabolism of life. It is tempting to imagine a shoreline at this time, a tide pool warmed by the morning light, filled with microbial mats layered like carpets. The surface layer is pigmented purple, absorbing one part of the spectrum. Beneath it lies a greenish layer, tuned to a different wavelength. Together they form a living filter, drawing energy from photons, producing sugars, growing, dividing. The water is still green with iron, the air still heavy with methane. But in that shallow pool, something fundamentally new is happening. Energy from beyond Earth is being pulled into the fabric of life. From our vantage point, we can see where this path would lead. Plants, algae, forests and fields, all descendants of those first experiments. But for the microbes themselves, it was simply another way of surviving. They had no foresight, no sense of history, only the blind evolutionary advantage of a metabolism that worked better than the alternatives. The haunting question that lingers is whether this was an accident unique to Earth, or a more general tendency of life anywhere. If microbes exist on another world, would they too find their way to pigments and photons? Or was the leap to photosynthesis a singular stroke of fortune? We cannot yet know. What we do know is that once it happened here, nothing was ever the same. The world of green seas and methane skies was on the verge of being rewritten, not by cataclysm from outside, but by the quiet persistence of microbes learning to eat the sun. Why didn't Earth fill with oxygen right away? When microbes first began to split water and release oxygen as waste, you might imagine the atmosphere quickly turning into something familiar to us today, rich in breathable gas, a sky turning blue with chemistry we could recognise. Yet the record shows otherwise. For hundreds of millions of years after photosynthesis began, oxygen stayed low, barely detectable, not the free and abundant molecule that would later transform the planet. The reason lies not in the failure of microbes, but in the hunger of the Earth itself. Every atom of oxygen released into the Archean seas was immediately captured. The oceans were loaded with ferrous iron, dissolved from the crust in an anoxic world where nothing had yet bound it into rust. This iron acted like an enormous sponge. When oxygen appeared, it reacted instantly, forming insoluble ferric oxides that settled to the seafloor. Instead of drifting upward into the air, oxygen was locked away in sediments as layers of iron minerals. The planet was rusting from the bottom up, quietly consuming each molecule of oxygen as soon as it was born. Sulfur too played its part. Volcanic gases released large quantities of reduced sulfur species such as hydrogen sulfide. In an atmosphere with little oxygen, these gases lingered. When free oxygen appeared, they reacted swiftly, producing sulfates and other compounds. Just as with iron, the sulfur cycle acted as a sink, mopping up oxygen and preventing it from accumulating. In this sense, the atmosphere was less like a reservoir and more like a battlefield, with every new oxygen molecule immediately attacked and consumed by eager chemical opponents. The mantle and crust provided a constant supply of these reduced materials. Volcanoes exhaled hydrogen, methane, carbon monoxide, and other oxygen-hungry gases. Each eruption added another wave of reducers into the sky and sea. The Earth's crust, still young and reactive, leaked iron and sulfur into circulation. Together, these inputs kept the balance tilted against free oxygen. No matter how much cyanobacteria released, the background chemistry absorbed it. It helps to think of the planet as having a series of enormous chemical debts. For billions of years before photosynthesis, reduced minerals had accumulated across the oceans and continents. Once oxygen production began, these debts had to be repaid. Every grain of ferrous iron, every molecule of hydrogen sulfide, every pocket of volcanic gas represented a claim on oxygen. Only after all these sinks were saturated could oxygen begin to linger in the atmosphere. The delay was therefore not a failure of biology, but the inertia of geochemistry. We can glimpse this interplay in the way rocks record oxidation states. Long before atmospheric oxygen became measurable, sediments show evidence of localized rusting. This tells us that oxygen existed, but only in microenvironments, quickly quenched before it could spread. Shallow lagoons or microbial mats may have had transient oxygen bubbles, but they never lasted. In a sense, the world was dotted with tiny islands of oxygen that vanished as soon as they touched the wider ocean or air. This drawn-out struggle also shaped the trajectory of life itself. Anaerobic organisms thrived during this interval because oxygen never rose high enough to threaten them on a global scale. At the same time, photosynthesizers kept producing, slowly tipping the balance. They were patient engineers, not conquerors. With every sunrise, more oxygen was made. With every nightfall, much of it was consumed. But over millions of years, the cumulative effect grew. Geochemists often describe this period as one of oxygen whiffs. These were not stable atmospheres, but temporary spikes, possibly lasting thousands of years, when oxygen briefly rose above background levels before being swallowed again. Evidence for these whiffs comes from trace signals in sediments, but the larger point is clear. Oxygen was trying to rise, and the Earth was trying to hold it back. The outcome would eventually be decided by whether biological production could outpace geochemical demand. Why was this balance so precarious? One reason lies in the energy of oxidation itself. Oxygen reacts strongly because it is one of the most electronegative elements, eager to pull electrons from other atoms. In the early Earth, nearly everything around was in a reduced state, loaded with electrons available for reaction. This made oxygen chemically irresistible. Imagine releasing a spark into a world filled with dry tinder. The spark cannot last, it always gets consumed. For oxygen, the early Earth was endless fuel. Eventually, this situation began to shift. Continual production by photosynthesizers slowly filled the sinks. Iron became locked into thick layers of oxide on the seafloor. Sulfur cycles adjusted, with sulfates gradually replacing reduced forms. Volcanic activity remained intense, but the overall inventory of reduced gases declined relative to the persistent production of oxygen. Little by little, the balance tipped. When the tipping point came, oxygen could finally accumulate faster than it was destroyed. But that was still far in the future. Between 2,700,000,000 and 2,400,000,000 years ago, the Earth was caught in the middle of this tug of war. It is humbling to consider how long this phase lasted. For humans, 1,000 years feels like deep history. For civilizations, even 10,000 years is almost unimaginable. Yet oxygen struggled against the planet's sinks for hundreds of millions of years, generation after generation of microbes producing, only to see their product vanish. Persistence, not speed, carried the day. What remains uncertain is exactly how the transition occurred. Did oxygen rise steadily as sinks were filled, or were there abrupt pulses, where local chemistry flipped suddenly, leading to brief global spikes? Different lines of evidence suggest different possibilities, and our understanding continues to evolve. What is certain is that the presence of these chemical sinks delayed the full impact of photosynthesis by an immense span of time. The haunting question is whether this delay was necessary. Could Earth have oxygenated earlier if the sinks had been smaller, or if photosynthesis had emerged later when the planet was less chemically reduced? Or was the timing inevitable, locked into the interplay between biology and geology? We do not know for sure. What we do know is that life and Earth were negotiating with each other, one producing, the other consuming, until the balance was finally broken. That balance, once tipped, would lead to one of the most dramatic transformations in planetary history. What kind of rocks remember a chemical war from billions of years ago? To find them, you would have to travel back to the shallow seas of the late Archean and early Paleoproterozoic eons, around 2,500,000,000 years ago, million to 2,400,000,000 years ago. In that world, the ocean was neither blue nor green as we know it today, but tinted by chemistry, carrying immense loads of dissolved iron. Into this ocean came a new presence, oxygen, born from photosynthetic microbes. What followed was less like a gradual mixing, and more like a battlefield, where each molecule of oxygen collided with iron atoms and left behind solid evidence in stone. That evidence is the banded iron formations, or BIFFs, some of the most striking rocks on Earth and a key record of our planet's early transformation. When oxygen first encountered the iron-rich seas, the reaction was immediate and dramatic. Dissolved ferrous iron, invisible in the water, oxidized into ferric iron, which could not remain dissolved. Instead, it precipitated as rust, tiny particles of iron oxide settling out of the water column. Over time, this process created thick deposits on the seafloor, layer upon layer of oxidized iron that hardened into rock. In places like Western Australia, South Africa and North America, these layers survive as bands of red, brown and grey stone, alternating stripes that stretch for metres, sometimes kilometres. They are the memory of an ancient ocean, recording the chemical war between oxygen and iron. The banding itself is still debated. Why should iron oxide and silica-rich chert appear in rhythmic alternation rather than as a single mass? Some scientists suggest that the bands reflect seasonal or cyclical variations in microbial activity. Perhaps during times of high photosynthetic productivity, oxygen levels spiked, oxidizing iron and depositing thick layers of hematite or magnetite. In quieter intervals with less oxygen, silica precipitated instead, forming chert. Others propose larger climatic or oceanographic cycles, tides of chemistry sweeping through ancient seas and leaving their imprint. The truth may be a combination of scales, from daily microbial rhythms to tectonic shifts. What matters most is that these formations are vast. Individual layers can be measured in centimetres, but entire deposits can reach hundreds of metres in thickness and extend across continents. They tell us that for a prolonged interval, Earth's oceans were the site of a massive rusting event, consuming oxygen and binding it into stone. Without this sink, oxygen might have risen faster in the atmosphere. Instead, it was pulled down into the seabed, forming the reddish stripes we now quarry as iron ore. Indeed, much of the steel that builds modern cities, railways and machines comes from mining these ancient rocks, relics of the Great Oxidation Event. In addition to their economic value, BIFs are a scientific gift. They provide a timeline of when oxygen began to accumulate in the environment, because their very existence depends on free oxygen. Before photosynthetic microbes, iron stayed dissolved as ferrous ions. After oxygen, it oxidized and precipitated. Thus, the sudden global appearance of BIFS signals the moment when oxygen production began to exceed local consumption, at least in shallow marine settings. It is a geological marker of biological innovation. Looking closely at the minerals within BIFS reveals even more detail. Hematite, magnetite, siderite, and greenolite appear in different proportions, depending on the chemistry of the water in which they formed. Some layers show evidence of microbial mediation, perhaps with bacteria helping to oxidize iron or reduce it again under anoxic conditions. This suggests that life was not merely a bystander, but an active participant in shaping the deposition of these layers. The rocks are therefore both chemical archives and biological ones, a record of the dialogue between microbes and minerals. What makes these formations so haunting is the scale of time they represent. Imagine a rain of rust falling slowly through the water column, day after day, century after century, until hundreds of meters of sediment accumulated. To build a single band might take thousands of years. To build an entire deposit might take tens of millions. And yet, over the vastness of geological time, they appear to us now as stripes of stone, compressed and silent. Each band is a pause, a pulse, a chemical heartbeat from an ocean that no longer exists. One of the puzzles still debated is why these formations appear globally at roughly the same time. From Canada's Superior Province to the Pilbara Craton of Australia, the story is the same. Around 2.5 to 2.33 billion years ago, the seas filled with iron oxides. This synchronicity suggests a planetary scale driver. Perhaps microbial photosynthesis had finally reached a tipping point, with oxygen production high enough to overwhelm local sinks. Perhaps tectonic shifts and continental weathering delivered vast new supplies of iron to the oceans, providing fuel for the reaction. Whatever the trigger, the outcome was global, leaving a signature we can still read today. The importance of BIFS extends beyond geology. They tell us that oxygen was not free to accumulate in the air until the oceans had absorbed their share. In effect, the seas were a giant chemical buffer, holding oxygen hostage until the iron was used up. This explains why there was such a long delay between the evolution of photosynthesis and the rise of an oxygenated atmosphere. The rocks remind us that life's innovations interact with Earth's reservoirs, and that the planet itself sets the tempo of change. There is also a poetic dimension here. The very metal we rely on for civilization was forged in an ancient catastrophe. Every time steel is smelted, every time iron is hammered into shape, we are working with minerals that originated in the first great struggle between oxygen and the ocean. Cities, bridges, and machines carry within them the memory of that ancient transformation. The past is not only in the rocks, but in the material of our daily lives. From a scientific perspective, BIFs are invaluable because they constrain models of the early atmosphere. Their chemistry requires oxygen, but not too much. If oxygen had been abundant everywhere, iron would have been stripped from the oceans too quickly. If it had been absent, iron would have remained dissolved. The persistence of BIF deposition over hundreds of millions of years indicates an intermediate world, with oxygen present but still limited, enough to precipitate iron yet not enough to saturate the environment. This balance is a key to understanding the tempo of Earth's early oxygenation. The haunting question is what it would have been like to witness those seas. Would they have appeared red, stained with iron particles, or would the rust have been invisible until it settled out? Would microbial mats have floated on the surface, producing oxygen while iron minerals drifted down like invisible snow? We cannot know for certain, but the rocks whisper that the oceans themselves were transformed, their chemistry rewritten in a way that no organism could ignore. The BIFs stand as monuments to this turning point. They are not just stripes in stone, but the residue of a global chemical war. A war that life itself began by releasing oxygen into a reduced world. And though we can study their minerals, measure their isotopes, and date their layers, they remain in some sense mysterious, relics of a world alien to ours yet foundational to everything that came after. What happened when oxygen finally escaped the oceans and entered the sky? For hundreds of millions of years, the oceans had been the great holding ground, pulling down every molecule of oxygen that life released. Iron was oxidized, sulfur was bound, volcanic gases consumed what they could. But around 2,400,000,000 years ago, the chemistry of the Earth shifted. The sinks grew saturated. The oceans had rusted enough. For the first time, oxygen began to slip free, climbing out of the seas and into the air. This moment, quiet and invisible at the time, marked one of the most profound turning points in the history of the planet. It was the beginning of an atmosphere that resembles our own. To imagine the world at that moment is to picture an alien landscape. The continents, still small and scattered, bore few traces of soil. Vegetation did not yet exist. The seas lapped against barren rock, dotted with microbial mats and stromatolite reefs. The sky was tinted not the clear blue we know, but likely hazy, with methane and carbon dioxide shaping its colours. Into this mix, oxygen began to seep. At first, the concentrations were tiny, fractions of a percent. But compared to the near-zero levels before, this was a revolution. The air itself was changing, gaining a new ingredient that would never again vanish completely. The first consequence of this new oxygen was chemical, not biological. Reduced minerals on the continents, long stable in the absence of oxidants, began to weather differently. Rocks containing iron sulfides now rusted at the surface, forming iron oxides that stained sediments red. Minerals that had been stable under anoxic conditions now altered when exposed to the open air. The chemistry of soils shifted. Drainage waters carried oxidized products into rivers and lakes. In subtle but far-reaching ways, the face of the continents changed colour. The Earth itself was beginning to wear the marks of oxidation. In the air, oxygen began to react with other gases. Methane, once abundant in the early atmosphere, was particularly vulnerable. Each oxygen molecule that collided with methane stripped it away, converting it into carbon dioxide and water. This was a profound change because methane is a far stronger greenhouse gas than carbon dioxide. As methane levels dropped, the climate system destabilized. For the first time, the chemistry of biology had the power to reshape the balance of heat across the planet. The stage was set for feedbacks between life and climate that would reverberate through deep time. Biologically, the escape of oxygen into the atmosphere marked the beginning of an ecological sorting. For anaerobic organisms that had thrived in the absence of oxygen, this new chemical presence was toxic. Oxygen is a reactive molecule, damaging proteins and membranes. Microbes adapted to an anoxic world faced a new stress, one they could not easily evade. Some retreated into refuges, buried in sediments, hidden in deep waters, or clinging to anoxic niches. Others perished, victims of what has sometimes been called the first global pollution crisis. For them, oxygen was not a gift, but a poison. For the organisms that could tolerate it, however, new opportunities appeared. Oxygen opened the door to metabolisms that yielded more energy. Respiration using oxygen as a terminal electron acceptor produces far more ATP per molecule of food than fermentation or anaerobic respiration. This meant that in the long run, lineages that adapted to oxygen could grow faster, evolve new complexities, and exploit new niches. The rise of atmospheric oxygen was therefore not only a crisis but a foundation for the future. The skies themselves must have changed in appearance. With even small amounts of oxygen present, ozone could begin to form high in the stratosphere. Ozone is made of 3 oxygen atoms, and it absorbs harmful ultraviolet radiation from the sun. Before oxygen, Earth's surface was bathed in far more UV light, which would have been dangerous to exposed life. With the beginnings of an ozone layer, protection became possible. Though it would take far longer for the ozone shield to fully stabilise, the process had begun. The evidence for this atmospheric transition lies in the rocks. Before the rise of oxygen, detrital grains of minerals like pyrite and uraninite could survive transport in rivers and be deposited in sediments. After oxygen began to accumulate, these minerals oxidised and vanished during weathering. Their disappearance from the geological record marks the point when oxygen was no longer confined to local niches, but had become an atmospheric presence. Similarly, the appearance of red beds, sediment stained with iron oxides, signals oxidation on land surfaces. Together, these records tell us that something fundamental had changed in the air around 2,400,000,000 years ago. It is worth remembering how small the change might have seemed at the time. Oxygen levels did not suddenly leap to modern values. They rose slowly, from essentially 0 to perhaps 1 or 2% of present atmospheric levels. To us, this would still be unbreathable. To life, then, it was revolutionary. Evolution rarely works in leaps. It works in thresholds. A small fraction of oxygen was enough to close the era of a fully anoxic world forever. There is humility in acknowledging that we do not know the precise tempo. Was the transition sharp, occurring within a few tens of millions of years, or more gradual, spread across hundreds of millions? Different lines of evidence suggest different answers. The geological record is patchy, and our interpretations are shaped by the rocks that happen to survive. Yet whether sudden or slow, the meaning is the same. Oxygen escaped, and the atmosphere was changed. The haunting question that arises is what it must have felt like to live through it. For microbes on a rock surface suddenly exposed to oxidizing air, the stress would have been immediate. For those hidden in deeper waters, the change might have been invisible. There were no eyes to see the new sky, no lungs to breathe the new air. And yet, for the first time, Earth's atmosphere carried the signature of biology in a way that would be permanent. The gases above were no longer only volcanic breath, but the waste of living things. That shift is one of the clearest markers of a living planet, and it began with this quiet escape. How can you prove the air changed 2 billion years ago without a time machine? That is one of the quiet marvels of geology. The planet itself has been recording its own biography in rocks, waiting for us to learn how to read it. The story of the Great Oxidation Event is not told in words or fossils of great beasts, but in subtle shifts of minerals, grains carried by rivers, and the changing colours of sediments. To us, these may look like ordinary stones, but they are the chemical diaries of Earth's surface, recording when oxygen first became part of the atmosphere in a meaningful way. One of the clearest signatures lies in rocks known as red beds. These are sandstones and mudstones stained with iron oxides, giving them their striking rust-red colour. Today, red rocks are not unusual, but before about 2,400,000,000 years ago, they are absent from the record. Their sudden appearance tells us that for the first time, oxygen was present in the air in high enough concentration to oxidize iron minerals at the surface. Iron that once weathered quietly in its reduced greyish forms now transformed into hematite and other oxides, locking into sediments as permanent stains. To geologists, this is not decoration. It is a signal that the chemistry of the atmosphere itself had crossed a threshold. Equally telling is the disappearance of minerals that should not survive in an oxygenated world. Pyrite, known as fool's gold, is an iron sulfide that is stable under anoxic conditions. In a world without oxygen, grains of pyrite eroded from bedrock could travel down rivers and be deposited in sandstones without oxidizing away. The same was true for uraninite, a uranium oxide that is stable only when oxygen is absent. Before the rise of oxygen, these detrital grains were found in sediments, carried like any other mineral. But after oxygen began to accumulate in the atmosphere, both pyrite and uraninite vanished from river and delta deposits. They could no longer make the journey from mountain to sea because the air and water along the way oxidized them into new compounds. Their absence is as loud as the presence of red beds. Together they tell us that oxygen had become a persistent feature of the surface environment. This combination of positive and negative evidence, the first appearance of iron-stained red sediments, and the simultaneous disappearance of reduced detrital minerals, is one of the strongest geological arguments for the Great Oxidation Event. It is not one outcrop or one region. These changes appear across continents, in rocks of the same age but scattered today across Africa, North America and beyond. The Earth system itself had shifted, and the mineralogical record is global. The challenge, of course, is that rocks do not come with labels. They do not announce, "Here begins oxygen." Geologists have had to build these interpretations step by step, comparing deposits, dating them, and asking whether alternative explanations could account for the evidence. Could red beds form without atmospheric oxygen? Could pyrite disappear for another reason? The answers so far suggest that while local conditions can vary, the global pattern points toward oxygenation. It is humbling, though, to admit that we are still piecing this together. Rocks that old are often altered, eroded or metamorphosed, and the signals we read are sometimes faint. The story is clear in broad strokes but still uncertain in detail. The appearance of red beds around 2,400,000,000 years ago is not just a marker of oxygen. It also reshaped Earth's surface processes. Oxidized soils weather differently than reduced ones. They hold nutrients in new ways, interact with groundwater differently, and change the cycling of elements. In subtle ways, oxygen in the atmosphere altered the geochemistry of the entire crust. Rivers carried different loads, sediments behaved differently when buried, and the balance of carbon and sulfur cycles shifted. This was not simply a change in the sky. It was a change in how land, water and atmosphere interacted at every level. Imagine the scene at the time. A river flowing off a bare craton, carrying sediments into a shallow sea. Before oxygen, its sands might include glittering pyrite grains, stable and inert. After oxygen, those same grains would tarnish, dissolve, and vanish before reaching the delta. Instead, the sands would be tinged with red, the iron in them locked into oxides. If you were a microbial mat growing in that delta, the sediment beneath your feet would literally look different from that of your ancestors. The change was not visible to eyes, because eyes had not yet evolved, but it was visible to the chemistry of the world. The absence of uraninite grains adds a deeper dimension. Uraninite is highly unstable in the presence of oxygen, oxidizing rapidly to soluble uranium species. Its disappearance from river deposits is one of the most powerful indicators that oxygen had spread into the atmosphere. Before, uranium grains could travel long distances without alteration. After, they vanished almost instantly, dissolved into water or transformed into secondary minerals. To find uraninite today in ancient sediments is to know you are looking at a world older than oxygen. To fail to find it in younger sediments is to know that the rules of chemistry had changed. Together, these lines of evidence provide a kind of before and after picture. Before, rivers carried reduced minerals intact, and sediments lacked the oxidized stains we know so well. After, those minerals were gone, and the red colours of iron oxides painted the land. This is how we know that air itself had changed. We cannot sample the atmosphere of the past directly, but the Earth was kind enough to leave these mineralogical fingerprints. Of course, nothing in science is absolute. The dating of these transitions is still debated, and not every region shows the same timing. Some geologists argue for earlier local oxygenation events, others for later global stabilization. The truth is probably that the Earth did not flip like a switch. Oxygen may have waxed and waned, rising locally, falling back, and only after millions of years becoming consistently established. Red beds and detrital grains tell us the broad story, but the fine details are still being written. The haunting question is whether this transition felt like a catastrophe or a quiet shift. For microbes poisoned by oxygen, it was certainly catastrophic. For the planet itself, it was silent, a change in chemistry rather than in scenery. Yet the record in the rocks is vivid. When you hold a piece of red sandstone from that era, you are literally holding a memory of the moment air changed forever. When you notice the absence of pyrite or uraninite, you're noticing the negative space left by a chemical revolution. That is how we know, without a time machine, that 2 billion years ago, the Earth breathed something new. Why do isotopes tell us secrets that fossils cannot? When we look back to the Great Oxidation Event, we are not dealing with a fossil record filled with shells, bones, or leaves. Life then was microscopic, soft-bodied, and rarely preserved in forms that survive in stone. But the chemistry of Earth's atmosphere left a different kind of archive, not in shapes, but in the ratios of isotopes locked into minerals. Among the most powerful of these archives are the isotopes of sulfur, which hold a record of how sunlight interacted with the early atmosphere, and how oxygen forever altered that interaction. Sulfur comes in several isotopic forms, each with a slightly different number of neutrons. Under most conditions, these isotopes behave predictably. Reactions tend to fractionate them by mass, with lighter isotopes reacting slightly faster than heavier ones. This is known as mass-dependent fractionation, or MDF. It is how sulfur behaves in modern Earth, and it is what most geochemists expect to see. But in rocks older than about 2,400,000,000 years, something unusual appears. Sulfur isotopes show mass-independent fractionation, or MIF. In these signatures, the isotopes deviate from the expected mass-based pattern, as if something in the atmosphere was bending the rules of chemistry. The cause lies in the interaction between ultraviolet light and volcanic sulfur gases in an oxygen-poor atmosphere. Without a protective ozone layer, ultraviolet radiation from the sun penetrated deep into the atmosphere, breaking apart sulfur dioxide molecules in ways that created exotic isotopic ratios. These photochemical products rained down onto the surface, where they were incorporated into sediments. The result was a sulfur isotope record with mass-independent patterns that cannot be explained by normal chemical reactions. It's as though the rocks were branded by the unfiltered sun. Then, around the time oxygen began to accumulate, the MIF signal disappeared. From 2,400,000,000 to 2,000,000,000 years ago, the sulfur isotope record transitions to purely mass-dependent fractionation, just like today. The explanation is simple yet profound. With oxygen in the atmosphere, an ozone layer formed in the stratosphere. That ozone absorbed much of the ultraviolet radiation that had once driven the strange MIF chemistry. With the UV flux cut off, the exotic fractionation ceased. From then onward, sulfur isotopes behaved normally, recording only mass-dependent processes. This shift is one of the clearest markers of the Great Oxidation Event. It is not a local feature, but a global one. Rocks from South Africa, Western Australia, Canada, and beyond all show the same transition. Before the event, MIF signals abound, after they vanish. The sulfur isotope record is therefore a time capsule of the atmosphere's chemistry, telling us when the sky became opaque to ultraviolet light. No fossils could tell us that story, only isotopes could. What makes this evidence especially compelling is that it connects biology, atmosphere and radiation in one signal. Photosynthetic microbes produced oxygen. That oxygen accumulated in the atmosphere. Ozone formed from oxygen, shielding the surface from ultraviolet light. The change in UV levels altered the chemistry of sulfur gases, erasing the MIF signal. Each step depends on the previous one. To see MIF disappear is to see oxygen's cascading influence, not only on life, but on the very physics of how sunlight interacts with air. Geologists studying these isotopes have to be careful. Rocks that old are often metamorphosed, and diagenesis can alter signals. But the consistency across multiple cratons gives confidence. The disappearance of MIF is not a quirk of one region, but a planetary shift. It is one of the rare moments in Earth's history where we can point to a specific line in the rock record and say, here, the sky changed. There are still uncertainties. How fast did the transition occur? Some records suggest it was rapid. others hint at fluctuations, with MIF signals persisting locally for a while before vanishing globally. This may reflect a patchy stepwise oxygenation, with pockets of a noxic atmosphere lingering in some regions, or it may simply reflect gaps in our sampling. As with much of deep time, the broad strokes are clear, but the fine details remain blurred. The significance of the sulfur isotope transition reaches beyond Earth. Astrobiologists note that MIF signals could be detectable in exoplanet atmospheres. A planet without oxygen and without an ozone layer might leave similar photochemical fingerprints in its sediments. Thus, what we learn from our own planet may help us interpret the signals of distant worlds. If we ever detect an alien rock record, the presence or absence of MIF could tell us whether that world has undergone its own oxidation event. There is also something quietly moving about the idea that sunlight itself left such a direct mark. Long before there were plants, long before there were animals, the sun's ultraviolet rays shaped the isotopic signatures that we can still measure today. And when oxygen arrived, the sun's imprint changed forever. In that sense, the rocks are not only a record of biology, but of the dance between a star and a planet. The haunting question is how life experienced this transition. Microbes at the surface may have found conditions less hostile once UV radiation was reduced, thanks to the ozone layer. Did new ecological niches open in shallow waters or on exposed surfaces? Did fewer DNA-damaging rays allow for more complex cellular structures to survive? We cannot know for sure, but the isotope record hints at more than chemistry. It hints at new opportunities for life, enabled by a sky transformed. In the end, sulfur isotopes tell us secrets that fossils cannot. They whisper of invisible radiation, of gases broken by light, of a shield rising in the stratosphere. They remind us that the Great Oxidation Event was not only a story of microbes and oceans, but also of atmosphere and sunlight, bound together in a feedback that changed the course of Earth's history. What's stranger than rocks that breathe? Rocks that change colour when the planet does? For geologists, some of the most puzzling evidence of Earth's atmospheric transition comes not from iron or sulfur, but from carbon itself. Carbon is the backbone of life, the main element shuffled through cells, buried in sediments, and exchanged between the atmosphere and oceans. And during the window between 2,400,000,000 and 2,000,000,000 years ago, the chemistry of carbon in rocks underwent an extraordinary and prolonged shift. This event is known as the Lomagundi-Getuli excursion, and it remains one of the largest isotopic anomalies in Earth's history. It is as if the entire biosphere leaned hard in one direction, leaving a chemical fingerprint in carbonates across the globe. The key clue lies in the ratio of carbon isotopes, specifically the heavier isotope carbon-13 compared to the lighter carbon-12. Normally, photosynthetic organisms prefer to take up carbon-12, leaving behind a relative enrichment of carbon-13 in the inorganic carbon pool. When these organisms die and are buried, the sediments that lock away their organic matter contain more of the lighter isotope, while the oceans and atmosphere reflect the leftover heavier one. It is a subtle process, but over long periods it shapes the isotopic record. During the Lomagundi-Getuli excursion, something amplified this process dramatically. Carbonate rocks deposited during this interval show unusually high carbon-13 values, far above the background levels of earlier and later times. What could drive such a shift? The simplest interpretation is that organic carbon burial increased on a massive scale. If more of the carbon-12 was being sequestered into sediments as organic matter, the remaining carbon pool would become heavier, enriched in carbon-13. In other words, vast amounts of organic carbon may have been locked away in sediments, tipping the isotopic balance. And because burial of organic matter effectively frees oxygen that would otherwise have been consumed during decay, this process would have allowed oxygen to accumulate in the atmosphere. The Lomagundi excursion may therefore represent not just a quirky isotopic blip, but the single largest oxygenation pulse in Earth's history. To imagine this in ecological terms, picture early microbial mats carpeting shallow seas. These mats were made up of photosynthetic bacteria, absorbing carbon dioxide, fixing carbon into their cells, and releasing oxygen. When portions of these mats died, their carbon-rich remains sometimes escaped decomposition and were buried in sediments. Multiply that process across vast continental shelves and shallow oceans, and you have the potential for extraordinary organic carbon burial. Every buried atom of carbon represented oxygen left free in the air. The scale of the Lumugunde excursion suggests that this process was global. Carbonates from Canada, Africa, Russia and India all show the same shift, meaning it was not just a regional accident of sedimentation. Instead, the entire carbon cycle of the planet was perturbed. This global coherence is part of what makes the excursion so striking. It lasted tens of millions of years, perhaps as long as 200 million, making it the longest sustained carbon isotope anomaly in Earth's history. The rocks from this time effectively record a prolonged interval of unusual carbon cycling, a planetary-scale experiment in oxygenation. Why did this happen when it did? One hypothesis points to the weathering of newly exposed continental crust. As oxygen built up in the atmosphere, sulfides and other reduced minerals on land began to oxidize, producing sulfate and driving chemical weathering. This weathering released nutrients such as phosphorus into rivers and oceans. With more phosphorus available, photosynthetic microbes could grow more rapidly, boosting productivity and organic burial. In this sense, oxygen and nutrient flux may have reinforced one another, creating a positive feedback loop. More oxygen enabled more weathering, more nutrients fueled more photosynthesis, and more burial freed even more oxygen. The Lumugunde excursion could have been the record of this runaway feedback, a time when the biosphere and geosphere pushed each other into new territory. Another interpretation involves tectonics. Around this time, continents were assembling into larger landmasses. Greater continental stability and wider continental shelves may have created ideal conditions for extensive carbonate deposition and organic carbon burial. The very architecture of Earth's surface may have conspired with microbial innovation to generate the excursion. It is worth noting, however, that while the isotopic shift is clear, the exact biological and geological mechanisms remain debated. Some researchers argue that the excursion reflects not only organic carbon burial, but also changes in the way carbon was cycled between reservoirs. For example, enhanced volcanism or changes in mantle outgassing could have altered the carbon supply. Others suggest that diagenetic processes may have exaggerated the signal in some rocks. The details are still being resolved, and the story is undoubtedly more complicated than a single cause. What is undeniable is the scale of the anomaly. At no other time in Earth's history do we see such a prolonged and pronounced enrichment in carbon-13. The Lumugunde excursion is therefore one of the strongest geochemical markers of the early Proterozoic, and it likely represents a time when oxygen levels reached a relative high point compared to the baseline before and after. Some have even suggested that oxygen concentrations may have briefly overshot, rising close to modern levels before later stabilizing at lower values. If so, the Earth may have briefly tasted an oxygen-rich future billions of years before animals ever evolved to use it. The legacy of the Lumugunde excursion is profound. It demonstrates that Earth's oxygenation was not a simple monotonic rise, but a dynamic and fluctuating process. Oxygen came in bursts and lulls, tied to feedbacks in the carbon cycle, tectonics, and microbial ecology. The excursion also shows how intimately life and Earth's geochemistry are connected. The burial of microscopic organisms could alter the isotopic balance of an entire planet and potentially change its atmospheric composition for hundreds of millions of years. The haunting question is why such a powerful positive feedback did not last forever. If organic carbon burial was fueling oxygenation, why did the process eventually slow down? What broke the cycle? For now, that question points us toward later intervals when the planet faced new challenges. But in this moment of Earth's history, the Lumugunde excursion stands as a reminder that the planet once breathed deeply, and the rocks themselves remember it in their isotopic colours. Could oxygen really have gone too far too fast? It seems almost impossible when we look around today and recognise how tightly balanced our atmosphere is. Roughly 1/5 of every breath you take is oxygen, stable enough that you rarely give it a thought. But when geologists peer back into the ancient record, they find signs that Earth's earliest brush with oxygen was not measured or cautious. It may have been excessive. Instead of a slow, incremental rise, oxygen may have surged during the early Proterozoic, briefly reaching levels that the planet would not see again for well over 1 billion years. If true, this overshoot hypothesis paints a picture of the Earth as a planet that lurched into the age of oxygen too quickly, destabilizing its systems in the process. The seeds of this idea come from the unusual magnitude and duration of the carbon isotope shift known as the Lomagundi-Getuli excursion. Carbonates from 2,300,000,000 to 2,100,000,000 years ago show extremely heavy carbon signatures, pointing toward extraordinary burial of organic carbon. Every unit of organic matter locked away represented a unit of oxygen left free in the air. If burial was as massive as the rocks suggest, oxygen could have spiked to concentrations far higher than previously imagined. Some models even suggest atmospheric oxygen may have climbed to near-modern levels, only to decline later. That possibility, that Earth tasted an oxygen-rich atmosphere and then backed away from it, is one of the most provocative ideas in paleobiogeochemistry. The overshoot hypothesis gains strength from multiple lines of circumstantial evidence. For one, the sudden disappearance of mass-independent sulfur isotope fractionation requires not just trace oxygen, but a substantial ozone layer. Ozone forms when oxygen levels climb to a few percent of present atmospheric concentrations. That alone marks a major threshold, but if oxygen surged higher still, the biosphere would have been transformed. For another, the geologic record from this interval shows widespread oxidative weathering of continental surfaces, red beds rich in iron oxides, and the scarcity of detrital minerals like pyrite and uraninite that can only survive in an anoxic world. Together, these signs suggest the planet was not just lightly dusted with oxygen, but thoroughly rusted. What would it mean for life if oxygen truly overshot? For anaerobic microbes, which had thrived in the billions of years before, such an atmosphere would have been catastrophic. Oxygen is reactive and damaging to cells without protective enzymes. For the newly established oxygen-producing cyanobacteria, however, this world would have been one they had created themselves. They may have flourished in the shallow seas, spreading across continental margins and driving the feedback loop of photosynthesis, burial, and further oxygenation. If the overshoot was real, then for a window of tens of millions of years, Earth may have been a microbial paradise bathed in sunlight and oxygen, with mats and films dominating the coasts. There is another implication. If oxygen reached near-modern levels this early, it suggests that Earth had the capacity to support complex multicellular life long before such organisms appeared. The Cambrian explosion, when animals rapidly diversified, would not happen until nearly 2 billion years later. So if oxygen was available, why did animals not evolve then? One answer might be timing. Eukaryotic cells themselves, with their nuclei and internal structures, were only just beginning to appear during this interval. They may not yet have been ready to capitalize on oxygen's potential. Another possibility is that the overshoot was temporary, a fleeting peak that quickly collapsed, leaving later eukaryotes without the oxygen they would eventually need. In either case, the overshoot hypothesis sharpens the puzzle of why complexity took so long to arrive. It is important to emphasize that the overshoot remains a hypothesis, not a settled fact. The geochemical signals can be interpreted in multiple ways, and there are uncertainties in correlating carbon isotope anomalies directly with oxygen concentrations. Burial of organic carbon is not the only process that can alter isotope ratios, and the preservation of signals over billions of years complicates matters. Some researchers argue that while oxygen clearly rose, the case for near-modern levels is overstated. The debate is ongoing, with new data from ancient sediments and improved models continually reshaping the story. What we do know is that the early Proterozoic was not a time of quiet equilibrium. It was a time when Earth's surface environments were shifting rapidly, perhaps lurching between states. To describe it as a feast is not far off. Oxygen surged, nutrients flushed into the seas, productivity soared, and the planet rusted. Such feasts rarely last forever. They carry within them the seeds of a later shortages, when the system can no longer sustain its own abundance. But in this moment, Earth may have reached its first true oxygen high. The haunting question is whether life remembered it. Did early eukaryotes emerge under skies richer in oxygen than their descendants would experience for the next billion years? Did they carry within them the adaptations forged in that fleeting high oxygen world? Or did the overshoot vanish too quickly to leave much trace in biology, written only in the isotopic quirks of ancient carbonate rocks? We cannot yet say, but the possibility that oxygen went too far, too fast, adds drama to a story already filled with upheaval. It reminds us that even something as life-giving as oxygen can destabilize when it arrives in excess. What happens when microbes invent a waste product they cannot survive in? This is one of the strangest ironies in the story of life. For nearly 2 billion years, microbes ruled Earth with metabolisms tuned to an oxygen-free world. They thrived on chemical gradients, pulling energy from hydrogen, sulfur, methane, and iron. Their world was alien to us, but perfectly stable for them. Then, a new metabolism emerged, one that could capture the inexhaustible energy of the sun. Cyanobacteria and their relatives began splitting water molecules to drive photosynthesis. The byproduct of that reaction was oxygen, an element almost absent from the environment until that point. Oxygen was not a useful fuel for those early microbes. It was a poison. To understand why, it helps to remember what oxygen does at a molecular level. Oxygen is highly reactive because it craves electrons. In cells without protective enzymes, oxygen tears through delicate biochemistry, breaking bonds, damaging proteins, and ripping apart DNA. To us it is invisible, something we take in without thought. To early anaerobes, it was a corrosive toxin. It was as if the planet had suddenly filled with bleach. For communities that had thrived in shallow waters, around hydrothermal vents, and across sediment surfaces, the rise of oxygen spelled disaster. The spread of oxygen was not immediate. Localized blooms of photosynthetic bacteria may have poisoned their own neighborhoods first. Imagine a mat of microbes in a coastal lagoon, pumping out oxygen as they captured sunlight. At first, the gas would have been consumed by iron in the water, rusting it into oxides. But once the iron was saturated, oxygen could accumulate. It would seep into the surrounding waters, then into the cells of neighbouring microbes. For anaerobes, the effect was lethal. Cells without enzymes like catalase or superoxide dismutase had no defence. Their membranes ruptured, their genetic code oxidised, their proteins unfolded. Entire communities collapsed. In this way, the first great die-offs may have been highly localised, playing out in shallow basins or tidal flats. But over time, as oxygen production grew and the sinks filled, the catastrophe scaled up. Oxygen began to spread into wider portions of the oceans and then into the atmosphere. This meant that anaerobes could no longer retreat simply by shifting to deeper water or migrating to new locations. The poison was everywhere. It crept into soils, surface waters, and eventually across whole continents. What had once been a hospitable planet for anaerobes became hostile in a geologically short span. We call the Great Oxidation Event one of Earth's first mass extinctions. It was not the dramatic asteroid impact that ended the dinosaurs, nor the sweeping volcanism that devastated the Permian world. It was slower and more insidious. It came not from outside the biosphere, but from within it. Life invented a waste product that was fatal to itself, and in doing so, life nearly exterminated much of its own diversity. Some studies suggest that as much as 99% of existing microbial lineages may have perished or been driven into extreme refuges during this time. If true, it was by far the most catastrophic biological bottleneck Earth had ever seen. Yet extinction was not absolute. Some anaerobes survived, and they did so by retreating into environments where oxygen could not reach. Deep sediments, groundwater aquifers, and hydrothermal vent systems remained largely anoxic. In these hidden refuges, ancient lineages endured. Even today, anaerobic microbes still thrive in such niches, reminders of a world long gone. Their survival shows that extinction was not total but selective. The rise of oxygen pushed life into new shapes, rewarding those that could adapt or hide. For the organisms that could tolerate oxygen, a new set of opportunities emerged. Some microbes evolved enzymes that detoxified reactive oxygen species, allowing them to survive in the presence of low concentrations. Others went further, learning to harness oxygen's reactivity for energy. Aerobic respiration, the metabolism that powers your own cells, evolved as a way to tame oxygen's dangerous appetite and turn it into a benefit. But in the earliest stages, before those adaptations were widespread, Oxygen was overwhelmingly destructive. It wiped out lineages that had persisted for more than 1 billion years. It reset the biosphere. The haunting part of this story is that it was not inevitable that cyanobacteria would win. Had other metabolisms proven more competitive, Earth might have remained an anaerobic world indefinitely. Complex life as we know it would never have evolved, because oxygen respiration provides far more energy than any anaerobic process. But from the perspective of the time, the success of oxygenic photosynthesis was catastrophic. It was an innovation that destabilized everything, a case of microbes fouling their own nest so thoroughly that most of them could no longer live in it. Geologists can see traces of this biological upheaval in the rock record. Alongside the geochemical signals of oxygen's rise, there is evidence of ecological turnover. Stromatolite diversity, once high, declines after the Great Oxidation Event. Microbial communities were disrupted, and only certain forms persisted. Though these patterns are difficult to reconstruct after billions of years, they hint at a biosphere in crisis, scrambling to adjust to a chemical revolution it had unleashed upon itself. There is a strange humility in this narrative. It reminds us that evolution is not guided toward improvement or balance. It is blind innovation, full of unintended consequences. Cyanobacteria did not set out to terraform the planet. They were simply finding a new way to harvest energy. The catastrophe that followed was collateral damage. From that damage, new pathways and new lineages would eventually rise. But in the moment, it must have felt like the end of the world for those microbes that had thrived since the Archean. The question that lingers is how often life does this to itself. Does innovation always carry the risk of self-destruction? On Earth, it happened with oxygen. Elsewhere in the cosmos, other metabolisms could play similar roles. If we ever detect biosignatures on distant planets, will we find records of catastrophic transitions where life poisoned its own world? For now, all we can say is that the Great Oxidation Event was both triumph and tragedy, invention and extinction. It was the moment when microbes created the conditions for future complexity by nearly killing themselves. One more layer of this story comes from looking at the quiet survivors that adapted rather than vanished. While many anaerobes succumbed to oxygen, others found inventive ways to live alongside it without fully abandoning their old chemistry. Some microbes developed strategies to shield themselves physically from oxygen by forming thick mats or biofilms, creating an internal microenvironment where their preferred anoxic conditions could persist. Within these layered structures, the surface cells might absorb or neutralize oxygen, allowing the deeper cells to continue functioning much as they had before. In this way, microbial communities became stratified worlds, each layer defined by its tolerance of oxygen. Other lineages developed biochemical tricks, such as pigments or proteins that acted as antioxidants, scavenging the dangerous reactive forms of oxygen before they could wreak havoc inside cells. These adaptations were not yet the full embrace of oxygen as a fuel source, but they marked an important step. They represent life inching toward coexistence with a molecule that had first appeared as a lethal pollutant. Each innovation widened the habitable envelope of the biosphere, ensuring that life could persist even as its environment shifted beyond recognition. In the longer view, the crisis also encouraged diversification. With many niches emptied by the extinction of anaerobes, those lineages that could endure or exploit oxygen had ecological room to spread. Evolution often accelerates after upheaval, when survivors inherit a world reshaped by catastrophe. This pattern, repeated again and again in later mass extinctions, may have had its first and most profound trial during the Great Oxidation Event. The biological turnover was not simply a cull, but a rearrangement of the entire microbial stage, with winners and losers decided by tolerance to a molecule that would define the planet from then on. Perhaps the most sobering thought is that this extinction left almost no visible trace. There are no skeletons to mourn, no forests turned to fossils. The victims were lineages of microbes, vanishing silently in sediments and shallow seas. The magnitude of loss is hard to picture, but it was real, a pruning of Earth's tree of life so severe that only a few branches remain to grow again. Every complex organism alive today descends from the sliver of diversity that squeezed through this oxygen bottleneck. In that sense, our very existence is built on the ruins of microbial worlds that could not withstand their own creation. The haunting question is whether those ancient microbes had the biochemical seeds of resistance that might, given more time, have saved them. Did they vanish simply because oxygen spread too fast? If the rise of oxygen had been slower, could more lineages have adapted instead of perishing? We cannot know. But it is a reminder that the pace of change matters as much as its direction, and that even in Earth's earliest history, survival often came down to timing as much as to innovation. Did oxygen almost end life instead of saving it? This is the paradox at the heart of one of Earth's earliest and most dramatic climate catastrophes. The Great Oxidation Event is usually remembered as the moment when oxygen finally spread into the atmosphere, setting the stage for complex life billions of years later. But oxygen is not only a breath of possibility, it is also a chemical disruptor, and when it reacted with other gases in the air, it may have driven Earth into one of its most extreme ice ages. This interval, known as the Huronian glaciation, lasted not for thousands of years, nor for 1,000,000, but for something closer to 300 million years. It is possible that this was the planet's first Snowball Earth, a time when ice may have stretched from the poles almost to the equator. To understand how oxygen could have triggered such a freeze, we need to look at what the atmosphere was like before. In the Archean world, long before oxygen was common, the main greenhouse gases were carbon dioxide and methane. Both trapped heat, but methane is especially powerful, molecule for molecule far more effective than carbon dioxide at insulating a planet. Under a faint young sun, when solar output was only about 70% of what it is today, methane may have been essential for keeping Earth liquid and habitable. Anaerobic microbes produced it in abundance, and it hung in the atmosphere as a warming blanket. When oxygen began to rise, this balance collapsed. Oxygen reacts with methane, breaking it down into carbon dioxide and water. Although carbon dioxide is a greenhouse gas, it is nowhere near as potent as methane. The net effect was a sharp drop in greenhouse warming. Imagine stripping away Earth's most important blanket just as the planet was finally beginning to rust. Suddenly, under the same weak sun, the surface lost much of its insulation. Temperatures fell, ice sheets advanced, and positive feedbacks amplified the freeze. White ice reflects more sunlight than darker land or ocean, so as ice spread, it cooled the planet further, creating a runaway process. Evidence for the Huronian glaciation comes from the rocks of Canada, South Africa, and other ancient cratons. Geologists find deposits called diamictites, chaotic mixtures of boulders, gravel, and fine sediment that are interpreted as glacial tillites, the debris left behind by advancing ice sheets. Some of these deposits contain dropstones, large clasts that seem to have fallen into fine marine sediments from floating icebergs. To see such features in rocks dated to around 2,400,000,000 years ago is a clear sign that glaciers were advancing far from the poles. For the first time in Earth's history, we have convincing evidence of ice sheets stretching across continents. What makes the Huronian glaciation extraordinary is not only its intensity but its duration. This was not a short-lived ice age. Multiple glacial episodes separated by brief warmer intervals seem to have stretched across hundreds of millions of years. For perspective, that is longer than the entire span between the extinction of the dinosaurs and today. The world may have been frozen and unfrozen repeatedly, a planet caught in cycles of ice and thaw, struggling to find a stable climate under the new rules oxygen had imposed. The consequences for life were severe. Photosynthetic microbes in shallow seas would have been entombed beneath ice, their access to sunlight cut off. Entire ecosystems could have collapsed as frozen oceans sealed away the energy of the sun. Anaerobic communities in the deep ocean might have fared better, buffered from the surface freeze, but even they would have faced disrupted chemistry as circulation patterns slowed beneath the ice. For life already struggling with the toxic effects of oxygen, the added blow of a global freeze may have pushed many lineages over the edge. And yet life did not vanish entirely. Some refugees must have persisted. Perhaps there were thin cracks in the ice where sunlight could still reach shallow waters. Perhaps volcanic islands poked through the frozen seas, creating oases of warmth and chemical flux. Hydrothermal vents would have continued to pump heat and nutrients into the deep ocean, offering safe havens for microbial communities. These scattered refugees could have sheltered the lineages that would later repopulate the world once the ice retreated. Still, the margin for survival must have been razor thin. It is humbling to imagine Earth under such conditions. A planet that today feels robust and forgiving was once so close to total collapse that only the hardiest microbes clinging to volcanic seeps and rare pools of open water kept the flame of life alive. If the freeze had gone further, if the ice had thickened to a point where no sunlight reached the seas at all, would life have endured? Or would Earth have become a sterile ball of ice circling the sun? The Huronian glaciation reminds us that survival in deep time was never guaranteed. What ended the freeze? Likely the same forces that end most global glaciations, the slow accumulation of carbon dioxide from volcanic outgassing. With oceans locked under ice, carbon dioxide could not be drawn down by weathering. Over millions of years, greenhouse gases built up until they finally tipped the balance back toward warmth. Ice retreated, seas opened, and the planet thawed. But the scars of the Huronian remained in the rocks, and its memory remains in our understanding of how fragile the climate can be. The haunting question is whether oxygen, the gas we depend on, nearly destroyed the very biosphere that created it. Was the Great Oxidation Event a gift to life, or was it almost its end? The Huronian glaciation forces us to see oxygen not just as a breath of life, but as a trigger for catastrophe. Life survived, but just barely, and in surviving it set the stage for the long road to complexity that would follow. The Huronian glaciation is more than just a tale of ice and oxygen. It is also a story of how interconnected Earth systems have always been. One of the most intriguing aspects is how continental arrangements may have magnified the freeze. During the Paleoproterozoic, large land masses had assembled near the equator. This meant that when glaciers advanced, they covered bright tropical ground, dramatically boosting the planet's reflectivity. Ice near the poles reflects sunlight, but ice on equatorial land reflects it even more effectively, amplifying cooling. In other words, the continents were in exactly the wrong place, at exactly the wrong time, tipping the balance further toward global ice. Another layer of complexity comes from the chemistry of the oceans beneath the ice. During long glaciations, circulation slows, and nutrients that would normally cycle back to surface waters remain trapped in the deep. This creates a nutrient famine, limiting productivity at the surface even if some patches of open water remained. When the ice finally retreated after millions of years, the oceans may have been primed for sudden bursts of microbial growth, fueled by the nutrients that had quietly accumulated. In this way, the very process of starvation may have set the stage for later recovery. The rocks of the Huronian not only tell us about the cold, but also about transitions in atmospheric chemistry. Interbedded with glacial deposits are layers rich in iron and other oxidized minerals, hinting at alternating phases when the atmosphere and oceans were briefly more oxygenated before plunging back into reducing conditions. It is as if Earth wavered between two unstable states, unable to settle into either a fully oxygenated world or a fully reducing one. These swings may explain why the glaciation came in pulses, rather than as one continuous deep freeze. There is also the question of how such a long glaciation reshaped the biosphere's evolutionary trajectory. Although no fossils of complex life appear from this time, the stress of such extreme conditions may have driven microbial innovation. Organisms that could endure freezing, tolerate low light, or exploit chemical energy sources would have had a selective advantage. Some researchers speculate that the Huronian could have acted as an evolutionary bottleneck, culling weaker lineages and favouring those with greater metabolic flexibility. If that is true, then the descendants of those survivors may have carried traits that ultimately proved useful as oxygen continued to reshape the world. From a modern perspective, the Huronian glaciation offers a sobering lesson. Climate can swing to extremes when one part of Earth's system shifts too quickly. Oxygen, methane, carbon dioxide, continental positions, and sunlight all played roles, showing that no single factor explains what happened. It was the interaction of all of them that locked the planet in ice. To think of Earth as resilient simply because it has endured for billions of years is to underestimate just how precarious survival has been. The haunting thought is that life's first great experiment with oxygen nearly smothered itself under ice. What does it mean that the very process that would one day allow animals to breathe also plunged the world into silence and frost? Perhaps the real story of the Huronian is that survival was never about inevitability, but about chance, refuge, and persistence in the face of planetary catastrophe. Life endured, but only just, and its endurance left a trail of frozen stones that still whisper of that deep time struggle. What did survival look like on a frozen, oxygen-poisoned planet? To imagine this chapter of Earth's history is to picture a biosphere reduced to scattered enclaves. A once busy microbial world collapsed into near silence. Around 2.5 to just over 2 billion years ago, oxygen was spreading into air and seas, methane was being stripped from the atmosphere, and ice had locked much of the planet into a state we call the Uranian glaciation. It is possible that as much as 99% of life on Earth vanished in the turmoil. What endured did so in isolated refuges, hidden away from the hostile new chemistry of the surface. One likely sanctuary was the deep ocean, where sunlight had never been the main source of energy. Long before oxygen appeared, microbes at hydrothermal vents and volcanic seeps had learned to build ecosystems on chemical reactions alone. These communities were powered by hydrogen, sulfur, methane, and iron released from the crust. Even when the surface froze and the atmosphere grew toxic, vents kept releasing heat and chemical fuel into the abyss. Around their mineral spires, mats of microbes and biofilms may have persisted as they had for hundreds of millions of years already, largely indifferent to what was happening above. If oxygen seeped down, it would have been diluted quickly or neutralized by reactions with volcanic gases. In this way, the deep ocean may have acted as a cradle that never froze, preserving at least a thread of the old anaerobic world. Other possible refuges were along volcanic coastlines, where heat and gases emerging from fissures could keep patches of water from icing over completely. Picture a world of white, silent seas with only rare spots of dark water, warmed faintly by geothermal activity. In these tiny oases, photosynthetic microbes may have clung on, producing oxygen even as most of their kind had perished. The balance between too much and too little oxygen would have been precarious. Some microbes might have hidden beneath layers of microbial mats, with surface layers absorbing the oxygen so that deeper layers could continue to live in reducing conditions. It would not have been a flourishing ecosystem, but it may have been enough to keep the lineage alive until conditions improved. Subglacial lakes offer another possibility. Modern Antarctica hides entire liquid water basins beneath kilometres of ice. If such features existed billions of years ago, they might have sheltered microbial life from both the freeze and the oxygen surge. Shielded from ultraviolet radiation, insulated from the cold, and buffered from atmospheric changes, these lakes could have hosted stable communities that outlasted the glaciation. We cannot yet confirm their presence in the Paleoproterozoic, but the analogy suggests how even an almost entirely frozen Earth could still harbour pockets of persistence. Geological evidence hints that rivers of meltwater sometimes flowed across the Huronian landscape. Seasonal thaws or volcanic eruptions may have carved brief pathways of liquid across otherwise frozen terrains. These transient environments might have supported short-lived blooms of microbial life, opportunistic bursts when conditions permitted. The microbes that could lie dormant, waiting for these rare windows, would have had an advantage, enduring long stretches of uninhabitable time before reawakening when water returned. Survival may have meant not continuous activity but patience on unimaginable scales. The toll of this bottleneck cannot be overstated. The majority of anaerobic lineages that had dominated the Archean world almost certainly disappeared. What persisted were the flexible ones, microbes able to tolerate a trace of oxygen, able to survive in cold, dark or chemically unusual environments, or able to enter states of dormancy that carried them through long millennia of famine. When scientists suggest that 99% of life was lost, it is not hyperbole. The Great Oxidation Event was as devastating to the microbial biosphere as any asteroid impact would later be for animals. But unlike the dramatic end of the dinosaurs, this was a slower suffocation and freeze, unfolding over millions of years. It leaves us with a haunting thought. The life that survived is the life we descend from. Every complex organism alive today can trace its ancestry back to those few microbial refuges that weathered the Huronian catastrophe. The branching diversity of the Archean biosphere is gone, erased by oxygen and ice. The lineages that endured carried forward not only their genes, but also the lessons of adaptation, mechanisms for coping with oxygen, strategies for endurance in cold and scarcity, that would later prove essential as Earth moved toward greater complexity. In this light, survival looks less like triumph and more like persistence in cracks and shadows. Earth at this time was not a thriving world, but a nearly silent one, punctuated only by isolated enclaves of microbial life. To us, those survivors may seem fragile and diminished, but in truth, they proved resilient beyond measure. Their endurance through such extremes ensured that life, once threatened with near extinction, could one day fill the world again. Another dimension to the survival story is the role of minerals and sediments as shields. In a world where free oxygen was toxic to much of life, protection could come not just from water or ice, but from the very mud and sand that blanketed microbial communities. In shallow seas, mats of cyanobacteria and other microbes often built stromatolites, layered, rock-like structures created by trapping and binding sediment grains. During the Great Oxidation Event, such mats may have doubled as fortresses, with deeper layers remaining cut off from oxygenated waters. The uppermost microbes bore the brunt of oxygen exposure, while those below continued living in the reducing conditions that matched their ancestry. Stromatolites, still found in some places today, may be living echoes of these ancient shelters. In certain basins, volcanic ashfalls or rapid sedimentation events could have entombed microbial mats and communities. To us this looks like catastrophe, but for microbes that tolerate low nutrient levels or enter dormant states, burial could have provided relief from oxygenated waters above. Within the sediment, gradients of chemistry persist, including anoxic microenvironments. These would have allowed fragments of anaerobic communities to persist in the shadows of oxygen spread. Though isolated and diminished, they could have bridged the gap between catastrophic surface change and future recovery. Even the chemistry of oxygen itself may have offered paradoxical havens. While oxygen gas was lethal in high concentrations, its reactivity meant that it often did not last long when it first met reduced materials like iron or sulfur. In local environments rich in such reduced compounds, oxygen would have been consumed quickly, creating oases of habitability just beneath the surface. Microbes in these zones could exploit the chemistry without being overwhelmed by it. These tiny pockets may have dotted coastlines and sediments, functioning like micro-refugees that together made the difference between extinction and survival. The cryosphere, too, may have played a subtler role in preservation. While ice sheets locked much of Earth into a deep freeze, they also acted as shields against ultraviolet radiation and cosmic rays. For microbial communities adapted to darkness and chemical energy, life beneath the ice could have been more stable than the volatile surface atmosphere. If sub-ice oceans existed, perhaps akin to the hidden seas of Europa or Enceladus today, they might have harboured stable microbial ecosystems, undisturbed by oxygen fluctuations above. What to us seems like entrapment in ice may have been, for some lineages, a sanctuary from oxygen's poison. Another avenue of resilience lies in the genetic flexibility of microbes. Even without fossils, we know from modern relatives that horizontal gene transfer, the swapping of genes between unrelated organisms, has long been a microbial strategy. During the Great Oxidation Event, as oxygen stress intensified, microbes able to acquire or share resistance genes, such as those encoding enzymes to detoxify reactive oxygen species, would have had a better chance at survival. This genetic fluidity may have seeded the first lineages that could do more than tolerate oxygen. They could begin to use it, laying foundations for the aerobic metabolisms that dominate today. Survival, then, was not just physical, but informational, hidden in the exchange of DNA fragments in ancient microbial mats and sediments. The overall picture that emerges is one of a planet reduced to scattered, humble refuges, mud layers, vent fields, under-ice lakes, sediment traps, and chemical gradients, all stitched together across vast spans of time. It reminds us that Earth's resilience lies not in unbroken continuity, but in the persistence of fragments. Each fragment of surviving life was fragile, but collectively they formed a thread strong enough to carry evolution forward. Perhaps the most haunting aspect of this survival is its invisibility. The fossil record does not show dramatic die-offs in this interval, only the quiet continuation of microbial traces. We infer the loss because of the scale of environmental change, because of the geochemical markers that tell us oxygen rose and methane fell, because the conditions would have been catastrophic for most lineages. But the survivors left so few visible imprints that it is as if the world passed through a silence in which only whispers of life remained. That silence, however, carried profound consequences. By reducing the biosphere to a narrow set of hardy survivors, the Great Oxidation Event may have simplified the playing field. The evolutionary experiments that came later, from the diversification of eukaryotes to the rise of animals, emerged from a world already stripped and pruned by catastrophe. In a way, every step of complexity we celebrate today rests on the survival of those hidden enclaves that endured through ice and oxygen 2 billion years ago. The question that lingers is unsettling. If 99% of life could vanish once, how many other near silences might be hidden in the deep past, erased by environmental shifts beyond our current evidence? And by extension, how much of what we think of as inevitable in evolution may simply be the residue of who happened to survive one catastrophe and not another? The Great Oxidation Event reminds us that survival is not guaranteed but contingent, precarious, and shaped by chance as much as by adaptation. If life almost died, how do we know about it now? The answer begins not in the depths of ancient oceans, but in the forests of 19th century North America, when a surveyor walked through Michigan and noticed something peculiar about his compass. In the year 1844, William Austin Burt was tasked with mapping land for settlers and logging companies. His compass needle wavered unpredictably, swinging away from true north as though some unseen force tugged at it. What he had stumbled upon was not a ghost or a trick of magnetism, but the exposed edge of one of the largest iron deposits on Earth. That chance observation would lead to mines, furnaces, railroads, and eventually to the recognition that these rocks recorded an event nearly 2.5 billion years old. By the late 19th century, explorers and miners were carving deep into the Mesabi, Marquette, and Gogebic ranges. They found not just iron, but a distinctive kind of rock, striped in alternating layers of red and grey. These were banded iron formations, or BIFs, quarried by dynamite and hauled away in rail cars, fueling the steel that built American cities and bridges. To the industrialists of the time, the stripes were simply a convenient source of ore. To geologists, they were puzzles written in stone. Why would layers of iron oxide be stacked with quartz-rich chert, repeated with such regularity and spread across whole continents? As the iron ranges were mined, specimens found their way into university collections and museums. The rocks were beautiful. Polished slabs gleamed with alternating ribbons of hematite red and grey quartz. At first, theories of their origin leaned toward the local and the practical. Some thought they represented volcanic eruptions that alternated with quieter sedimentary periods. Others suggested they were chemical precipitates from odd lakes. But as geological mapping expanded, it became clear that banded iron formations were not regional quirks. They occurred across North America, Africa, Australia, and beyond, all dating back to the same general window of deep time. Their scale alone suggested that something global had been at work. By the early 20th century, advances in stratigraphy allowed geologists to place the BIFS within a broader framework of Earth's history. Fossils were sparse in these ancient rocks, but radiometric dating and correlation tied them to the Paleo-Proterozoic. This was the first hint that the iron layers might represent a world different from our own, a time when the chemistry of the oceans and atmosphere was profoundly unlike today. As laboratories improved, scientists began to probe their chemistry in detail. They noticed that the iron oxides required an oxidant, something to strip electrons from dissolved ferrous iron and lock it into solid minerals. But what could have provided that oxidant billions of years ago, before plants or animals existed? The answer took shape slowly, as pieces from different disciplines converged. Microbiologists had already discovered photosynthetic bacteria, some of which produced oxygen as a byproduct. Sedimentologists noted that the timing of iron deposition coincided with other signals of environmental change. Put together, the case strengthened. These vast layers of iron were not accidents of local geology, but the frozen signatures of oxygen flooding ancient seas. The red bands were the chemical graves of dissolved iron reacting with oxygen for the first time on a planetary scale. It is striking that one of Earth's most important biological revolutions is known to us largely because of its waste products. The oxygen itself dissipated into the air. The microbes that produced it left almost no recognizable fossils. But the iron they rusted out of the oceans settled in quiet layers that miners would later dynamite for steel. Every bridge girder and skyscraper beam forged from those ores is, in a sense, a monument to cyanobacteria that lived billions of years ago. We know about the near death of life because modern civilization accidentally unearthed its record. Yet even now, the interpretation is not complete. Scientists debate exactly how the alternating layers formed, whether they reflect seasonal changes, pulses of microbial activity, or larger oscillations in Earth's chemistry. Some bands may represent storms or volcanic events that stirred nutrients into the ocean, feeding photosynthetic bacteria. Others may mark quiet intervals when oxygen production slowed. Each stripe, only centimetres thick, could represent thousands of years. Taken together, the BIFS span hundreds of millions of years, a slow testimony to the balance between life, oxygen, and ocean chemistry. The story also reminds us of how human curiosity builds from unexpected beginnings. A surveyor's faulty compass, an industrialist's hunger for ore, a geologist's puzzlement at stripes in stone, all converged to reveal that Earth had nearly frozen, and that oxygen had almost killed the world that produced it. The rocks were silent until we learned to read them, and they remain one of the most enduring records of the Great Oxidation Event. The haunting question is how many other global cataclysms are written into Earth's crust in ways we have not yet deciphered. If banded iron formations could hide in plain sight as building material for centuries, what other testimonies lie underfoot, waiting for the right eyes and tools to translate them? The fascination with these rocks deepened as scientists realized they were not just static relics, but dynamic records of Earth's earliest experiments in planetary transformation. By the mid-20th century, geologists began comparing BIFS with modern environments where iron still precipitates, such as hydrothermal vents and certain iron-rich lakes. These analogues suggested that ancient oceans must have been loaded with dissolved iron in amounts unimaginable today. When oxygen entered those waters, the iron crashed out in great chemical rainfalls, forming deposits thick enough to be quarried billions of years later. The sheer abundance of these formations hinted at oceans that were not just streaked with rust, but saturated with it, a world whose chemistry was fundamentally alien to us. As mining intensified in the 20th century, entire landscapes were reshaped by the excavation of iron. Gigantic open pits like those in Minnesota's Mesabi Range or Western Australia's Pilbara revealed cross-sections of banded layers stretching for kilometres. Each pit wall became, unintentionally, a window into deep time. For local communities, these mines fueled economies and steelworks. For science, they opened vast laboratories of exposed rock where the signatures of ancient oxygenation could be studied at unprecedented scales. Students, geologists and paleobiologists alike walked among the stripped walls, tracing layers that once lay under shallow seas. There is something humbling about the way industrial need and scientific curiosity intersected here. The very act of extraction that powered human industry also uncovered the archives of Earth's first atmospheric revolution. When miners cut into those rocks, they revealed evidence not only of wealth, but of the survival of life itself. Without these mining operations, our understanding of the Great Oxidation Event might have developed more slowly, pieced together only from scattered outcrops. Instead, the scale of industrial excavation brought the phenomenon into sharp focus, making its global extent undeniable. Even beyond their scientific value, the BIFS have inspired awe for their beauty. Polished slabs are sold as decorative stones, their stripes gleaming in shades of red, silver and black. In homes and museums, they sit as art objects, quietly carrying a record of catastrophic change from over 2 billion years ago. Few people who admire their symmetry realize they are looking at the residue of an ancient environmental crisis, one that nearly extinguished the very possibility of complex life. This juxtaposition between beauty, utility and catastrophe is part of what makes them such powerful symbols. Today, when scientists reconstruct the history of the Great Oxidation Event, they lean heavily on the archives opened by miners and surveyors more than a century ago. The banded iron formations became the Rosetta Stone for interpreting a time when oxygen was both destroyer and saviour. The fact that their story emerged only because a compass needle once twitched in the Michigan woods underscores the role of chance in human discovery. It raises the unsettling thought that perhaps much of what we know about Earth's past depends not only on the persistence of rocks, but on our luck in stumbling across the right ones. What if rocks could whisper about ancient air? At first glance, the stones we step over or stack into walls appear mute, inert, and utterly divorced from the history of breath. Yet buried within them are subtle patterns in atoms that act as codes, chemical traces of the atmosphere that once enveloped this planet. Modern isotope science has become the craft of listening to those whispers. With no fossils of lungs or leaves from over 2 billion years ago, scientists have turned instead to the ratios of sulfur, oxygen, and even barium isotopes as proxies. These tiny variations are not random. They preserve the fingerprint of ancient reactions between gases, minerals, and life. Sulfur isotopes were among the first to reveal just how different early Earth's atmosphere must have been. In the absence of oxygen, ultraviolet radiation from the sun split sulfur dioxide molecules high in the sky, in ways that left behind a mass-independent fractionation signature, something that simply does not occur under today's oxygen-rich conditions. When sulfur-bearing minerals with that anomalous signal show up in rocks, we know they must have formed in an atmosphere without much free oxygen. After the Great Oxidation Event, those strange signals vanish, replaced by the mass-dependent fractionation we see in all more recent sediments. The rocks cannot tell us what the air smelled like, but they can tell us what the chemistry of sunlight and gas allowed. Oxygen isotopes provide another avenue. Water molecules contain oxygen, and when conditions shift, whether through evaporation, glaciation, or biological activity, the ratio of oxygen 16 to oxygen 18 can tilt in predictable ways. Ancient rocks bearing these isotopic signatures let scientists reconstruct not just the presence of free oxygen, but also how it cycled through glaciers, oceans, and the atmosphere. Some of the earliest evidence of glaciation, including during the Huronian Ice Age, comes from such isotopic patterns. It is as though the very ice, long vanished, left behind an echo in the balance of oxygen atoms trapped in minerals. Barium isotopes have recently joined this detective's toolkit. Though less well known than sulfur or oxygen, barium can carry signals of ocean chemistry, particularly when tied to cycles of productivity and burial of organic matter. Subtle shifts in the relative abundance of barium isotopes in marine sediments provide clues about whether the oceans were oxygenated, stratified, or dominated by microbial recycling. While no single element gives the whole story, taken together these isotope systems allow a multi-angled reconstruction of conditions too ancient for direct observation. The brilliance of isotope science lies in its humility. No one line of evidence is definitive. Every ratio requires careful interpretation. Every measurement is just one data point in a sea of uncertainty. Yet when sulfur anomalies disappear worldwide at roughly the same interval, when oxygen isotopes hint at global ice, and when other elements echo similar transitions, the pattern becomes persuasive. It is not a single whisper, but a chorus of minerals repeating the same refrain. Earth's air changed in a way it never had before. There is also a human beauty in this approach. The ability to read isotope ratios at such precision is only decades old, the product of mass spectrometers capable of distinguishing parts per million in atomic weights. With such tools, modern scientists have reached back billions of years, far beyond any written record, beyond even the oldest fossils of recognizable cells, to infer the chemistry of the sky itself. It is the closest thing we have to a time machine, not through wires and gears, but through atoms locked into stone. Yet these chemical codes remain open to interpretation. Different labs, different outcrops, and different contexts sometimes yield results that challenge one another. Was the oxygen rise abrupt or stepwise? Did sulfur cycling change everywhere at once, or did patches of the planet remain anoxic? The rocks do not answer directly. They murmur and we listen, comparing whispers from South African cratons, Canadian shield outcrops, and Russian cores. Each carries part of the truth, and together they sketch a world in transition. The haunting question, then, is not simply whether we can reconstruct what happened, but how much of the story we may still be missing. If isotopes are whispers, What parts of Earth's early air have left no trace at all? How many chemical languages are we still deaf to? Our tools grow sharper each decade, but humility reminds us that even in stone, much of deep time may remain forever silent. What isotope science also teaches us is patience. The signals scientists extract are not bold headlines, but faint margins written into stone over incomprehensible spans of time. Consider how a single volcanic eruption today leaves a measurable but fleeting fingerprint in the atmosphere. In the deep past, eruptions were constant, weathering never ceased, and microbes churned chemical cycles in every tide pool. To distinguish one background process from the grand shifts of the Great Oxidation Event requires comparing many records across many continents. It is only through this careful collation that broad narratives emerge. One of the most striking revelations from isotope work is the unevenness of the oxygen transition. The disappearance of sulfur's mass-independent signals may feel like a clean cut-off, but closer inspection reveals complexity. Some basins appear to have oxygenated earlier, others lagged behind. What we call the Great Oxidation Event may have been less a single moment than a staggered patchwork of local experiments, stitched together over tens of millions of years. The isotopes record this unevenness like multiple witnesses recalling the same event from different vantage points, none identical but together convincing. Scientists also look beyond sulfur and oxygen to elements such as selenium, chromium, and iron isotopes. Each system responds differently to redox conditions, the balance between oxidizing and reducing environments. Chromium, for instance, is mobilized during oxidative weathering on land and carried into the oceans, where its isotopic ratio shifts depending on whether it is deposited under oxic or anoxic conditions. These subtle differences, imperceptible to the eye, tell researchers whether rivers carried oxygen's imprint into the seas. When combined with barium or molybdenum records, a richer picture emerges of not just the air above but the water below. Isotope science does more than confirm that oxygen rose. It also allows scientists to test competing hypotheses about why. Was oxygen accumulation tied mainly to microbial innovation, to tectonic cycles that delivered nutrients, or to the exhaustion of geochemical sinks? Each scenario should leave a slightly different isotopic legacy. For example, a world where weathering of continents suddenly accelerated would show enhanced delivery of sulfate to the oceans, recorded in sulfur isotopes. A world where organic carbon burial surged would mark carbon isotope excursions. These chemical detectives are not perfect, but together they narrow the possibilities, giving us some confidence that we are not simply weaving stories from coincidence. Another virtue of isotope records is their ability to capture feedbacks, how one change triggered others. When oxygen began to accumulate, it not only altered the atmosphere but also shifted nutrient cycles, weathering rates, and even the reflectivity of the planet's surface. These knock-on effects left signatures in multiple isotope systems at once. By comparing them, researchers can see whether a spike in oxygen coincided with, for example, intensified phosphorus delivery or cooling trends tied to methane loss. The rocks whisper not just about air but about the cascade of consequences that followed. There is a poetic irony here. The very atoms we breathe today were once partitioned into strange ratios that betray past climates and atmospheres. Inhaled through our lungs, oxygen is invisible and weightless. Measured in a laboratory, oxygen isotopes become a time-stamped message from a world that no longer exists. To think that every glass of water, every gust of wind, and every flake of snow carries within it a distribution of isotopes shaped by ancient and modern processes alike is to recognize how deeply time saturates the present. Yet even isotope science has limits. Rocks must be preserved, undisturbed, and accessible to record these patterns. Vast regions of Earth's crust have been recycled by plate tectonics, their chemical histories erased. What survives is partial, selective, and sometimes ambiguous. The whispers are patchy, their grammar difficult. We may never know whether we are reconstructing a symphony or a fragment. But even fragments can change how we understand the story of life, reminding us that survival depended on balancing at the edge of chemical thresholds we're only beginning to decipher. The haunting question is whether future scientists, perhaps billions of years from now, will read the isotopic remnants of our own age. Will they see the unmistakable spike of carbon isotopes from fossil fuel burning? Will they hear in that signal the whisper of a species that altered its atmosphere knowingly, rather than by accident? If isotopes are the language of air trapped in stone, then our words are already being written. What ended the Great Oxidation Feast and started a billion-year famine? To understand this moment, we have to picture a world in which oxygen had briefly surged, perhaps more dramatically than it ever would again until animals appeared. After hundreds of millions of years of slow accumulation and geochemical wrestling matches between microbes and minerals, the atmosphere had tipped into a new state. Oxygen, for the first time in Earth's history, became a dominant atmospheric player. The oceans recorded it in layers of iron, and the continents recorded it in rust-red rocks. It was a time of apparent expansion, of photosynthetic microbes flourishing across shallow seas. And then, abruptly, the growth faltered. The feast ended not with a smooth decline, but with a collapse so sharp that researchers call it one of the most dramatic contractions in the entire history of the biosphere. Evidence for this downturn comes not from fossils, those were still far too rare and simple, but from isotopic markers and unusual minerals that captured the chemistry of ancient seas and skies. In recent years, studies of ancient barite deposits in Canada's Belcher Islands have revealed oxygen isotope anomalies so striking that they point directly to a catastrophic drop in biological productivity. These are known as delta-17 oxygen anomalies, and they reflect processes in the atmosphere that only make sense when coupled with large swings in the size of the living world. At their peak, they suggest that biological productivity may have crashed by more than 80%. Imagine an entire planet's worth of microbial mats, surface scums, and shallow water photosynthesizers shriveling away, leaving only remnants clinging on. The biosphere itself had shrunk to a shadow of its former size. The Hotchkiss study that highlighted these anomalies reframed how scientists view the end of the Great Oxidation Event. Rather than being a steady rise toward modernity, the oxygen story is punctuated by sudden crashes. The barites of the Belcher Islands, laid down in shallow seas over 2 billion years ago, preserve trapped sulfur and oxygen isotopes that serve as a geochemical diary. Within their crystals, the oxygen isotope ratios tell of a world suddenly deprived of photosynthetic input, a system where the very cycling of gases through the atmosphere changed character. These are whispers from a biosphere in crisis, locked in minerals harder than granite, carried through eons until human hands cut them open with diamond saws. Why did this famine follow so closely on the heels of a feast? One hypothesis points to the very success of oxygenation itself. When photosynthesizers stripped carbon dioxide from the air and methane from the skies, they triggered not only glaciations but also nutrient starvation. The burst of oxygen that had seemed like a triumph may have burned through resources unsustainably. Just as modern algal blooms in lakes collapse once nutrients are exhausted, so too may the global microbial community have overshot its limits. The isotopic record suggests that the fall was not just local or temporary, but global, sustained, and severe. This collapse had consequences beyond biology. With productivity diminished, the burial of organic carbon slowed. That, in turn, reduced the release of oxygen into the air, weakening the atmosphere's newfound oxygen blanket. Earth did not plunge back into its fully anoxic state, but the high point of the Great Oxidation was gone. For more than 1 billion years afterward, oxygen levels remained low, patchy and unstable, leaving life to adapt within narrow bounds. Some have called this long interval Earth's boring billion, though it was hardly boring for the organisms struggling to persist under its constraints. To picture the biosphere's contraction is to imagine the planet itself dimming. Shallow seas that once shimmered with microbial mats may have become bare mudflats. Water columns that once supported active cycles of photosynthesis and respiration may have turned sluggish, dominated again by anaerobic chemistries. Even the colour of the oceans could have shifted, green with iron or dark with sulfide, reflecting a retreat from the brief experiment in oxygen-driven productivity. The world was not lifeless, but it was quieter, simpler, and far more fragile. The haunting question is what this teaches us about planetary thresholds. Did life nearly snuff itself out by producing too much oxygen too quickly, destabilizing the very environment it depended upon? Was the crash inevitable, or was it the unlucky product of tectonic chemical and biological coincidences? We cannot know for certain, but the Belcher barytes suggest that even the most promising revolutions in Earth's history have stumbled. The Great Oxidation Feast gave way to famine, and life endured in reduced form for an expanse of time longer than all of human history multiplied 100 times. The image of an 80% collapse in global productivity is so staggering that it forces us to think carefully about what productivity really meant in the world of 2 billion years ago. At that time, the vast majority of primary production, the conversion of sunlight and chemicals into organic matter, was carried out by microscopic communities carpeting shallow shelves or drifting as invisible plankton in the upper water column. There were no forests, no grasses, no fish to graze, only mats of single-celled organisms quietly turning light and dissolved gases into the building blocks of food chains. To say that this living skin shrank by 4/5 is to imagine entire coastlines stripped bare, lagoons emptied of their photosynthetic haze, and the planet's total output of life's fuel reduced to a fraction of what it had been. The isotopic fingerprints found in ancient barytes are compelling because they capture not just local quirks but global shifts in how gases cycled between air, sea, and rock. Oxygen isotopes carry the mark of how much photosynthesis was happening, and when they swing wildly, it suggests that the biological pump moving carbon, sulfur, and oxygen through the Earth system faltered on a planetary scale. The patterns cannot be explained by volcanic eruptions alone, nor by a single continent's weathering pulse. Instead, they speak to a biosphere that had been stretched thin by its own rapid transformation. Some scientists frame this collapse as a kind of planetary correction. The Great Oxidation, in this view, was an exuberant overshoot. Cyanobacteria and their kin flooded the environment with oxygen, altering the balance of greenhouse gases, shifting the acidity of waters, and rusting out entire oceans. But the Earth system is not an unlimited sink. Nutrients like phosphorus, essential to photosynthesis, may have been rapidly depleted by the boom. When those supplies dwindled, the microbial world could not maintain its former pace. What followed was a drawdown, not to zero, but to a new equilibrium at much lower levels of activity. The isotope record suggests this adjustment was severe and enduring. It is worth emphasizing that this was not extinction in the sense we are accustomed to from later times. The collapse was not about losing distinct lineages so much as losing scale. Microbes endured, clinging to vents, coasts, and sediments, but they no longer covered the world with the same abundance. The ecological fabric thinned, the energy flow through ecosystems slackened, and Earth entered a quieter rhythm. In a strange way, this thinning may have set the stage for the future. The persistence of life in lean times tested metabolic flexibility, rewarding lineages that could adapt to low oxygen conditions while still eking out energy from light or chemical gradients. The Belcher barytes, then, are not just mineral curiosities. They are time capsules of crisis, preserving in their crystals a record of a biosphere that ballooned and then deflated. When geologists first pried them from the rocks, they could not have known they were holding evidence for what may have been the deepest famine life had ever endured. Only through the patient decoding of isotope ratios did these minerals begin to tell their story. They remind us that progress in Earth's history is not linear. Even revolutions like the rise of oxygen can stumble, collapse, and linger in diminished states for spans of time so vast they defy human imagination. The haunting question is what it felt like, if we can use that phrase for a microbial world, for the Earth to dim in this way. Did the seas, once streaked with rusty clouds and microbial scums, grow clearer, more sterile, less alive? Did the very soundscape of the planet, the crackling, bubbling mats that formed as microbes vented gases, fall silent? We cannot know, but the isotopic scars in the rocks suggest that something fundamental in the pulse of life slowed, and it would not quicken again for over 1 billion years. Why did Earth stay poor in oxygen for over 1 billion years? It is one of the most puzzling questions in the story of our planet, because once oxygen had made its first great leap into the atmosphere during the Great Oxidation Event, one might expect the trend to continue steadily upward. Instead, for nearly half of Earth's entire history, oxygen remained scarce, atmospheric levels hovering at a fraction of what they are today. This long interval, stretching from about 2 billion to about 1 billion years ago, is often called the mid-Proterozoic, and it has been described with the unflattering nickname of the boring billion. Yet there was nothing boring about it. It was a time when the planet's chemistry, biology and climate were locked into a delicate balance, one that throttled the flow of oxygen into the sky and kept life constrained to relatively simple forms. The key to this prolonged oxygen poverty seems to lie in nutrients, particularly phosphorus. Phosphorus is one of the central elements in biology, a backbone of DNA and RNA, a component of cell membranes, and the spark in the molecules that carry energy around living systems. Without phosphorus, cells cannot divide efficiently, cannot build sturdy genetic material, and cannot sustain the metabolic machinery that makes photosynthesis possible. In short, phosphorus is life's bottleneck, and during the mid-Proterozoic, that bottleneck appears to have been very narrow. Geologists studying ancient sediments have found signs that phosphorus delivery to the oceans was limited. Weathering of continental rocks is the main way phosphorus enters the marine system, and when that weathering is sluggish, the seas are starved of this essential nutrient. With little phosphorus available, photosynthetic microbes could not multiply in the dense blooms needed to flood the atmosphere with oxygen. Productivity slowed, oxygen production lagged, and the biosphere settled into a quiet state, supporting only a fraction, perhaps as little as 6%, of the biological output we see on Earth today. The oceans themselves may have reinforced this low oxygen stasis. Evidence suggests that vast stretches of the mid-Proterozoic seas were not only anoxic but also enriched in dissolved iron and sulfide. These so-called ferruginous and euxinic waters would have acted like traps, locking up phosphorus in chemical reactions and pulling it out of circulation. Microbes in the shallows may have worked diligently to photosynthesize, but much of the oxygen they produced would have been consumed by reactions with reduced chemicals in the water before it could escape into the air. The deep ocean thus functioned as a vast oxygen sink, maintaining a cap on atmospheric accumulation. This chemical landscape also influenced the kind of life that could persist. Complex eukaryotic cells, which would eventually give rise to algae, fungi, plants and animals, seem to have appeared during this interval, but they remained marginal players. Without abundant oxygen, and with nutrients scarce, they could not expand into large ecosystems. Instead, microbial mats and prokaryotic plankton continued to dominate, their productivity limited, their diversity constrained. Fossil evidence from this time is sparse, and most of what we know comes from geochemical proxies rather than visible remains. The Earth was alive, but it was subdued, ticking along in low gear. Why did this state persist for so long? One reason may be tectonic stability. During this billion-year interval, the continents drifted slowly, and supercontinents like Nuna and later Rodinia formed and broke apart at a languid pace. Without frequent massive eruptions or dramatic mountain-building events, the supply of fresh rock to weather was limited. Less fresh rock meant less phosphorus delivered to the oceans, and the nutrient famine continued. The Earth system had locked into a feedback loop. Low weathering kept nutrients scarce, scarce nutrients kept productivity low, and low productivity kept oxygen in check. From a human perspective, a billion years is an incomprehensible span of time. It is more than 200 times the age of our species, longer than the entire history of the animals on this planet. To imagine the Earth under a ceiling of limited oxygen for that length of time is to picture a biosphere whose pace of change was glacial, whose innovations were stifled before they could expand. Yet within this constraint, evolution did not stop. It simmered, preparing lineages that would one day take advantage of oxygen's return. The haunting question is whether the mid-Proterozoic world was a planet stuck, or a planet incubating. Was life stalled by circumstance, unable to climb higher until tectonics and chemistry allowed, or was it quietly building the capacities that would later bloom? We may never know for certain. What we do know is that the Earth's great oxygen famine endured for over 1 billion years, a reminder that progress in deep time is not guaranteed. Even revolutions like the rise of oxygen can be slowed to a crawl, leaving a planet breathing shallowly while the clock of geology ticks on. If we lean closer to this mid-Proterozoic world, what emerges is not simply a picture of lifeless stagnation, but of a planet that had slipped into a finely balanced state. On one side of the balance was the slow weathering of ancient continental crust, dribbling phosphorus into the oceans in such meagre amounts that microbial populations could never explode beyond modest scales. On the other side were the chemical sinks of the seas themselves, iron and sulfide waiting to mop up both oxygen and phosphorus whenever they became too abundant. This double constraint made the biosphere feel like it was trapped beneath a glass ceiling, unable to expand, unable to innovate at the pace it might otherwise have done. To imagine daily existence during this interval is to think of a biosphere that pulsed, but never surged. Microbial mats would have continued to spread across shallow shorelines, their communities feeding on sunlight, fixing carbon, and releasing oxygen locally into the water. Yet those bursts of oxygen were immediately countered by reactions with reduced chemicals, particularly in the iron-rich deeper basins. Like sparks falling on wet tinder, they flared briefly and then fizzled out. The atmosphere above, though not devoid of oxygen, would have contained only a fraction of today's concentration, likely less than 1% of present atmospheric levels for vast stretches of this billion years. The air was breathable only for microbes adapted to oxygen scarcity, and for most anaerobes, it remained threatening. This long interval also produced one of the most striking puzzles in Earth history: the first hints of eukaryotes. Molecular fossils and rare microscopic remains suggest that complex cells with internal structures had begun to evolve during this time. These cells demanded more energy than prokaryotes, and oxygen was the fuel that could have supported them. Yet with oxygen availability capped, these lineages seem to have lingered in the background, unable to radiate widely. Their existence during the so-called boring billion shows that life was experimenting, but the environment simply was not yet ready to support their expansion. It is almost as if the Earth had given life a new tool but withheld the resources to wield it fully. Geochemists sometimes describe this interval as one of nutrient starvation. Phosphorus in particular appears to have been recycled tightly within the oceans. When organisms died and sank, their phosphorus-bearing compounds were often locked away by chemical reactions in the sediments. Little was returned to circulation, and so the next generation of microbes had even less to work with. In modern oceans, storms and currents churn nutrients back into surface waters, fueling new productivity, but in the mid-Proterozoic seas, that recycling seems to have been inefficient. Productivity therefore remained low, reinforcing the long oxygen famine. From a broader perspective, the mid-Proterozoic reminds us that Earth's history is not a story of inevitable upward progress. For over 1 billion years the planet existed in a kind of stasis, with oxygen present but capped, life diverse but limited, and evolutionary potential waiting for the right conditions. It was a world of immense patience. The rocks deposited during this time, shales, carbonates, and iron formations, bear witness to a biosphere that persisted in slow motion. They are monotonous to the human eye precisely because the Earth system itself was locked into monotony. The haunting question that emerges is whether such long plateaus are common on habitable worlds elsewhere. If a planet can remain locked for 1 billion years in a nutrient famine, what does that mean for the likelihood of complex life evolving elsewhere in the cosmos? The Earth eventually escaped its oxygen ceiling, but there was no guarantee it would. The mid-Proterozoic stands as a reminder that the path from microbial mats to multicellular life is not straightforward. It can pause, stall, and linger in low gear for almost unfathomable spans of time. That it eventually broke free tells us something profound. Patience, persistence, and the right geological nudges can eventually shift the balance. But for over 1 billion years, Earth was a world that breathed shallowly, its oxygen rationed, its life restrained. What killed the iron bands and replaced them with black shales? For hundreds of millions of years, the oceans had been a theatre of chemical warfare between oxygen produced in the shallows and the dissolved iron lurking in the depths. The results of that conflict were painted into the seafloor in the form of banded iron formations, alternating layers of rust-red oxides and pale cherts. Then, around 1,900,000,000 to 1,800,000,000 years ago, this familiar rhythm abruptly ceased. The iron bands that had once been laid down with almost clockwork regularity dwindled away, never to return on the same scale. In their place, new kinds of sediments emerged. Dark, organic, rich shales suffused with iron sulfide minerals. This change marked the birth of a different ocean, one that has been called the Canfield Ocean, after geochemist Donald Canfield, who first pieced together its chemistry. The culprit was sulphur. As continental weathering increased under the oxygenated skies of the Paleoproterozoic, rivers delivered vast amounts of sulfate into the seas. Sulfate is highly soluble, and once it entered the marine system, it opened a new metabolic niche. Certain groups of microbes learned to reduce sulfate, turning it into sulfide as part of their energy metabolism. This process, known as bacterial sulfate reduction, is still common in today's marine sediments, but in the Proterozoic it took on a planetary scale. The influx of sulfate and the expansion of these microbes filled the oceans with hydrogen sulfide, a gas toxic to most forms of life and potent in its chemical effects. Hydrogen sulfide reacts eagerly with iron, forming iron sulfide minerals like pyrite. Where once oxygen had combined with iron to produce rust-red oxides, sulfide now stole that role, precipitating black opaque minerals that were locked into shales. The classic red bands of the earlier oceans disappeared, replaced by dark layers recording a sulfidic chemistry. This shift effectively ended the reign of banded iron formations. The oceans had moved into a new regime, one in which the deep waters were no longer simply anoxic but actively poisonous, saturated with sulfide. The Canfield Ocean was not uniform. Surface waters, in contact with the air, still held some oxygen, and shallow microbial mats continued their photosynthetic work. But below a certain depth, the chemistry flipped. The deep ocean was hostile, stratified, and sulfidic, and the boundary between these layers may have shifted with climate and circulation. It was a strange world, neither the iron-rich seas of the Archean nor the fully oxygenated oceans of later eons, but something in between. Life had to navigate this patchwork environment, thriving in narrow zones of safety and retreating from the black depths where sulfide dominated. The evidence for this transition lies in the rocks. The disappearance of large-scale banded iron formations around 1,850,000,000 years ago coincides with the appearance of widespread black shales rich in pyrite. Geochemical analyses of these shales reveal not only high sulfur content, but also isotopic signatures consistent with bacterial sulfate reduction. This is the forensic trail that allows scientists to reconstruct the chemistry of oceans long vanished. The pattern is global, suggesting that the Canfield Ocean was not a local quirk, but a planetary state that endured for much of the mid-Proterozoic. Why did this shift matter so much? Because it altered the availability of nutrients and the pathways of energy in the biosphere. Sulfide-rich waters limited the distribution of oxygen, suppressing the expansion of more complex life that might have otherwise taken advantage of oxygen's rise. They also scavenged trace metals essential to cellular processes, further tightening the nutrient bottleneck. The oceans had found yet another way to restrain the growth of productivity and to cap the levels of oxygen in the atmosphere. The haunting question is whether this sulfidic world was inevitable once oxygen began to reshape the continents. Did the weathering of sulfide-bearing minerals on land guarantee that the seas would eventually fill with sulfate and that microbes would inevitably exploit it? Or could Earth's trajectory have unfolded differently, skipping the long detour through the Canfield Ocean? We do not know, but the rocks suggest that for nearly 1 billion years, this sulfidic state dominated the deep. It was a hidden chapter in the oxygen story, one that explains why the rise of oxygen stalled for so long. The iron bands had vanished, but in their absence, the Earth was not idle. It was brewing a new chemical ocean, one whose memory is etched in black stone. Why didn't animals evolve right after oxygen first appeared? If oxygen was the great gift of the early Proterozoic, one might imagine that its arrival would have sparked an immediate flowering of complex life. After all, oxygen fuels the most efficient form of cellular respiration known, providing more energy per molecule than any other metabolism. It underpins the activity of large bodies, rapid movement, and the coordination of many specialized cell types. So why, after the first big rise in oxygen around 2 billion years ago, did Earth remain a world of single-celled organisms for well over 1 billion years? The answer lies in the frustratingly incomplete nature of the oxygen revolution itself. Although the Great Oxidation Event marked the beginning of free oxygen in the atmosphere, levels never rose anywhere near modern values. At their peak, they may have reached about 10% of what we breathe today, and at times they likely fell well below that. Such concentrations were enough to rust rocks, oxidize sulfides, and support patches of aerobic metabolism, but they were not enough to sustain large, energy-hungry organisms on a global scale. Complex multicellular life requires a reliable, planet-wide supply of oxygen above a critical threshold. The mid-Proterozoic simply did not deliver that. The oceans, too, tell us why complexity stalled. For hundreds of millions of years after the Great Oxidation, the deep seas remained anoxic. Surface layers carried some oxygen, but beneath them the waters were still rich in iron, or later, saturated with sulfide in the Canfield Ocean state. This meant that most of the ocean's volume, the great bulk of its water mass, was off-limits to oxygen-using life. Only a shallow skin along the continental margins could have supported aerobic metabolisms, while the depths remained hostile. This narrow band of habitability effectively capped the expansion of complex life, forcing it into tiny ecological corners rather than letting it spread freely across the planet. Within this limited framework, evolution still pushed forward. Eukaryotic cells, organisms with nuclei, internal membranes, and more sophisticated metabolisms appeared and diversified. Fossil evidence suggests their presence by at least 1,800,000,000 years ago, and molecular markers confirm their persistence throughout the so-called boring billion years. Yet these eukaryotes remained small, microscopic, and relatively simple. Without abundant oxygen, their energetic advantage could not translate into large body size or multicellular complexity. They were experiments waiting for the environment to catch up. This long delay highlights how finely tuned life is to the planet's chemistry. It is not enough to have oxygen in principle. It must be abundant, widespread, and stable. The mid-Proterozoic atmosphere wavered below that threshold, and the deep oceans actively suppressed further accumulation. Nutrient limitations compounded the problem. Phosphorus, the backbone of genetic and metabolic molecules, was in short supply, and recycling within the seas often trapped it instead of making it available for new productivity. With nutrients scarce and oxygen capped, the biosphere limped along at a fraction of its possible energy output. To call this billion-year stretch boring is misleading, because it was a time when the rules of the Earth system were being rewritten in slow motion. Continents shifted, supercontinents assembled, mountain belts rose and eroded, and the deep chemistry of the oceans cycled between iron-rich and sulfur-rich states. But to the eye of an observer, if one had existed, there would have been little visible difference. No forests, no animals, no large algae drifting in the seas. The world remained microbial, a planet of small, patient cells waiting for the next great push. The haunting question is whether complex life could ever have emerged under such marginal conditions. Was the rise of animals delayed simply because oxygen and nutrients were scarce? Or were there deeper evolutionary hurdles that took time to overcome? We cannot disentangle these possibilities entirely. What we do know is that oxygen did not act like a switch, instantly turning on complexity. It acted more like a slow lever, raising the ceiling gradually while life pressed against it. For more than 1 billion years, that ceiling remained too low. The long pause between the appearance of oxygen and the rise of animals invites us to look beyond simple chemistry and consider the constraints of ecosystems themselves. In a world dominated by microbes, competition often rewards efficiency at the microscopic scale. Single-celled organisms reproduce quickly, adapt swiftly, and need only minimal resources. In such a context, the evolutionary payoff for building larger multicellular bodies was small, especially when the environment could not guarantee enough oxygen to support those experiments. So even though the genetic machinery for complexity may have existed, natural selection tended to favour strategies that kept organisms small and flexible. The sedimentary record hints at this microbial dominance. Stromatolites, those layered structures built by bacterial mats, thrived across shallow seas during the mid-Proterozoic. They represent communities of microorganisms, often cyanobacteria, that trapped sediments and built up stony mounds over time. Stromatolites had existed since the Archean, but during this boring billion, they became especially widespread, suggesting that microbial ecosystems were well adapted to the low oxygen, low nutrient world. In essence, Life had reached an equilibrium suited to its environment, and that equilibrium resisted disruption for vast spans of time. At the same time, there is evidence of subtle innovation beneath the surface. Microscopic fossils known as acritarchs, likely representing early eukaryotic plankton, appear and diversify during this period. Their tough organic walls suggest adaptations for surviving in fluctuating environments, perhaps enduring long stretches of scarcity. Some of these microfossils show hints of ornamentation, spines or processes that may have been used for defense or to alter buoyancy. These features hint at ecological interactions beyond simple photosynthesis, perhaps including grazing and predation at the microbial scale. Even in a world that seemed stagnant from afar, evolutionary experiments were taking place in miniature. Geochemistry reinforces this picture of a constrained but not motionless biosphere. Trace metal abundances, including molybdenum and iron, suggest that while oxygen was present in surface waters, deeper basins remained starved of it. This stratification kept recycling processes inefficient. Organic matter that sank into deeper waters often met anoxic or sulfidic conditions, where it was degraded without releasing its phosphorus and nitrogen back into circulation. In this way, the chemistry of the oceans locked away nutrients that could have fueled more productivity, maintaining the biosphere in a state of arrested development. From a planetary perspective, the persistence of such conditions may have been stabilized by feedbacks. If oxygen levels rose slightly, oxidative weathering on land might have increased, but so too would the burial of organic matter and sulfides that drew oxygen back down. If productivity surged briefly, the nutrient reservoirs were quickly depleted, pulling it back into balance. This self-regulating system meant that Earth remained stuck in a narrow band of low productivity for over 1 billion years. To break free, something fundamental had to change in the coupling of geology and biology. Looking back, it is tempting to view this interval as a long prelude to the age of animals, but we should resist the urge to treat it as mere waiting. For the organisms alive at the time, this was the whole story: their world, their equilibrium, their version of thriving. What seems like a billion-year delay to us was simply the natural outcome of Earth's environmental constraints. Complexity was possible in principle, but the stage was not yet prepared. The haunting thought is how many evolutionary pathways may have been explored and abandoned in that span. How many lineages of small, almost complex organisms arose only to disappear without ever leaving a visible trace? What if the Great Oxidation was never truly great in the sense of being finished, but rather the first act in a much longer story? The rocks and isotopes suggest that oxygenation was not a single, irreversible revolution, but a stepwise process that unfolded over nearly 2 billion years, each rise punctuated by stalls and setbacks. The initial surge around 2.4 billion years ago flooded the surface with new chemistry, but as we have seen, it was followed by long periods of famine, stagnation, and partial retreat. Earth's atmosphere and oceans became oxygenated enough to leave unmistakable traces in the geologic record, yet they never climbed to the levels that would support large and energy-hungry organisms. In other words, the Great Oxidation may have been only the first chapter in a serial tale of atmospheric transformation. Evidence for this stepwise model comes from both geology and geochemistry. After the initial rise, oxygen appears to have hovered at relatively low levels, fluctuating through the mid-Proterozoic, sometimes dipping back toward near-anoxic states. Sedimentary deposits reveal episodes where sulfidic waters expanded across continental margins, replacing oxygen with hydrogen sulfide. These Canfield-style conditions persisted in many basins for hundreds of millions of years, reinforcing the sense that oxygenation was not a one-way climb but a fragile balance that could tip backwards. Trace metal records, particularly molybdenum and chromium, register pulses of oxygenation followed by declines, as if Earth's biosphere and crust were negotiating over who would control the available redox balance. By the late Neoproterozoic, roughly between 800 and 600 million years ago, the chemical signals sharpen again. Carbon isotopes, trace metal enrichments, and sulfur records point to another major oxygenation pulse, often called the Neoproterozoic Oxidation Event. This rise appears to have been more durable and widespread than the Great Oxidation Event, pushing oxygen concentrations closer to modern fractions. It is in this window that the atmosphere and surface ocean finally appear to have sustained enough free oxygen to alter ecosystems in fundamental ways. If the earlier event could be described as a revolution half completed, the later event seems to have been the one that opened the door more fully. The stepwise pattern raises haunting questions about causation. Why did Earth not leap directly from an anoxic to an oxygen-rich state? One answer lies in nutrient dynamics, with phosphorus availability controlling the size of the biosphere. Another answer lies in the slow chemical weathering of the continents, which gradually adjusted the balance of reduced minerals able to soak up oxygen. Each tectonic shift, each glaciation, each burst of volcanic outgassing may have nudged the system toward or away from stability. The consequence was a long tug-of-war that only settled after more than 1 billion years of fluctuations. For scientists, the comparison between the Paleoproterozoic Great Oxidation and the Neoproterozoic Oxidation Event provides perspective. The first marks the crossing of a threshold from a reducing world into one where oxygen could accumulate at all. The second marks the deepening of that change into something closer to permanence. They are connected episodes, separated by geological ages, but part of a single grand trajectory. To imagine the Great Oxidation as final is to miss that it was only a beginning, a precarious foothold on the path toward the atmosphere we rely on today. The haunting question remains: if Earth required multiple oxygenations, could it just as easily have stumbled and failed along the way? The idea of stepwise oxygenation also invites us to think of Earth as a system that does not always move in straight lines. Feedbacks, thresholds, and delays create long plateaus and sudden leaps. After the first surge, the atmosphere did not simply stabilise at a new higher level, but instead entered an era of oscillation. Some geochemical records hint at intervals when oxygen in shallow seas may have been surprisingly abundant, only to collapse again when the underlying drivers faltered. These repeated surges and setbacks resemble the fragile balance of a campfire. It can flare brightly with a rush of air and dry wood, but if the fuel is damp or scattered, the flames dwindle back to smoke. One way to sense these ancient flickers is by examining the isotopic fingerprints of molybdenum and uranium. In oxygen-rich oceans, these metals dissolve and cycle widely. In oxygen-poor seas, they are stripped out and locked in sediments. The patchy record of their concentrations across the mid-Proterozoic suggests that some basins may have temporarily hosted oxygenated surface waters, while others sank back into anoxia. These spatial contrasts imply that Earth's oxygenation was not uniform. The planet could be simultaneously breathable in one region and suffocating in another. Such unevenness would have been bewildering for life trying to push into new forms of complexity, for stability and consistency were as important as abundance. Another line of evidence comes from glaciations that punctuated the Proterozoic. At least twice in the Neoproterozoic, ice sheets may have reached equatorial latitudes, creating so-called Snowball Earth conditions. These global freezes would have scoured continents, altering nutrient fluxes, while also reshaping atmospheric chemistry. When the ice retreated, weathering delivered bursts of phosphorus and other elements into the oceans, perhaps fueling productivity and drawing down carbon dioxide. Such episodes may have tipped the balance toward higher oxygen, locking in the gains of the Neoproterozoic Oxidation Event. In this view, oxygenation was not a smooth ascent, but a ladder of icy rungs, each crisis resetting the system and opening the way for a more oxygenated equilibrium afterward. It is also striking that the Neoproterozoic Oxidation Event coincides with the appearance of large-scale sedimentary phosphorus deposits. These rocks hint that the nutrient cycle itself was shifting. If the Great Oxidation Event had run into the ceiling of nutrient scarcity, the later pulse may have been helped by tectonic reorganizations and biological innovations that liberated more phosphorus into the oceans. The arrival of eukaryotic algae with efficient nutrient uptake strategies may also have changed the game, allowing oxygen production to ramp up in ways that earlier microbial mats could not achieve. Thinking of these two oxidation events side by side, the earlier one seems almost like a rehearsal, an incomplete experiment that revealed both the possibilities and the limits of Earth's biosphere. The later one, though separated by more than 1 billion years, feels like the culmination of lessons learned by the planet itself. The haunting possibility is that Earth's oxygenation was never guaranteed. A different balance of volcanic gases, a longer persistence of sulfidic oceans or a delay in tectonic nutrient delivery might have kept the atmosphere trapped in semi-anoxia indefinitely. If so, the planet would have remained a microbial world, rich in chemistry but barren of animals. What emerges is not a story of one decisive revolution, but of a series of attempts, failures, and eventual success. The Great Oxidation Event is the first step, the one that taught the Earth system how to oxygenate at all. The Neoproterozoic oxidation is the second step, the one that finally pushed oxygen to levels sufficient to alter ecosystems irreversibly. Both are reminders that planetary change often requires persistence. Life and geology do not simply change once and stop. They adjust, retreat, and advance again. The unsettling question is whether our own atmosphere today, so rich in oxygen, is more stable than those earlier intervals, or whether even now we stand on balances as fragile as those of deep time. What does it take to turn oxygen into animals? At first glance, the question might seem simple, but when stretched across hundreds of millions of years, it becomes one of the most profound mysteries in Earth history. Around 800 million years ago, the atmosphere was still a shadow of what it would eventually become. Oxygen hovered at levels far below modern concentrations, perhaps 10 to 15% of today's values, and deep oceans remained patchily anoxic. Yet in this interval, something began to stir that would permanently alter the trajectory of life. Tiny eukaryotes, cells with nuclei, organelles, and greater internal complexity had been evolving for more than 1 billion years, but they had remained largely limited in size and ecological impact. Then, almost as if released from a chemical constraint, they began to diversify into larger forms that left recognizable fossils, heralding the world of animals. The key to this transition lay in energy. Complex multicellular organisms require enormous amounts of it compared to their single-celled cousins. Constructing tissues, coordinating cells, and maintaining communication networks within a body are expensive tasks. Oxygen respiration provides far more energy per unit of food than fermentation or anaerobic metabolism ever could. For billions of years, microbes had eked out an existence using strategies that worked but placed a cap on size and complexity. With a sufficient rise in oxygen, organisms could afford to experiment with becoming bigger, more specialized, and more interactive with their environments. In this way, oxygen was not the sole cause of animals, but it was the precondition that made their existence possible. The evidence for this great shift appears in multiple forms. Fossil assemblages from Namibia, Newfoundland, and China preserve the enigmatic Ediacaran biota, creatures that emerged between 600 and 5 million years ago, 140 million years ago. Some resemble quilted mattresses, others frond-like organisms rooted to the seafloor. While their precise relationships to later animals remain debated, their size alone speaks to a new ecological reality. No purely anaerobic biosphere could sustain such macroscopic life. In parallel, molecular clocks calibrated with genetic data suggest that lineages leading to sponges, Cnidarians and bilaterians began diverging during this same oxygen-rich interval. Together, these lines of evidence support the view that the Neoproterozoic oxidation event provided the energetic push for multicellular animal evolution. It was not just oxygen levels that mattered, but also their stability. Earlier in the Proterozoic, shallow seas may have seen temporary pulses of oxygenation, only for conditions to relapse into anoxia. For animals to thrive, environments needed to remain oxygenated long enough to sustain complex food webs. By around 800 million years ago, geochemical records of chromium isotopes and rare earth elements suggest that more persistent oxic conditions had spread into continental margins and shallow shelves. These were precisely the habitats where early animals could anchor themselves and filter feed. The ocean was no longer a patchwork of transient chemical oases. It was becoming a consistently breathable space. The story deepens when considering Snowball Earth episodes that bracketed this transition. Twice in the Neoproterozoic, ice sheets may have covered the globe almost to the equator. These freezes would have devastated ecosystems, but also profoundly altered nutrient cycling. When the ice finally retreated, vast amounts of freshly weathered rock supplied phosphorus to the oceans, fueling blooms of photosynthetic organisms. Those blooms pumped out oxygen, which then reinforced the gains of the Neoproterozoic oxidation. Paradoxically, catastrophe may have set the stage for innovation. Life was nearly extinguished, but in recovering it surged into new niches. One might ask why animals did not appear immediately after oxygen levels first rose 2 billion years earlier. The answer lies in thresholds. Partial oxygenation is not enough. For macroscopic animals, the oxygen minimum required to diffuse into tissues and fuel-active metabolisms is substantially higher than for microbes. The Great Oxidation Event gave Earth perhaps 10% of its modern atmospheric oxygen, but this was insufficient for large multicellular animals. Only with the later stepwise increase, approaching 20 to 30% of today's levels, did the physiological barrier finally break. Complexity was no longer chemically forbidden. This perspective also reframes the Cambrian explosion that followed soon after, around 540 million years ago. Rather than a sudden miracle, it becomes the culmination of a long oxygen apprenticeship. For more than 1 billion years, life had hovered in the wings, limited by chemistry. Then, when oxygen crossed a threshold, biological potential that had been building quietly erupted into evolutionary fireworks. From sponges filtering seawater to the earliest predators pursuing prey, animals began to shape ecosystems with a force unseen before. Oxygen had become not just a gas in the sky, but the currency of complexity. Yet even here, humility is necessary. Oxygen alone cannot explain everything. The fossil record shows bursts of innovation coinciding with environmental shifts, but the exact cause and effect relationships remain tangled. Genetic innovations, ecological interactions, and planetary feedbacks all played roles. Oxygen was the enabling backdrop, the invisible scaffold against which the drama unfolded. Without it, animals could not have risen. With it, they finally could. The haunting question is whether this transition was inevitable on any oxygenated world, or whether it required the peculiar chain of accidents that shaped Earth. If oxygen is common in the universe, should we expect other planets to give rise to animals? Or is our story a rare exception carved out of 1 billion years of near silence? If oxygen nearly killed us once, what keeps it safe for us now? It is easy to forget that the gas we breathe is not guaranteed by physics alone. It is the outcome of a precarious balance between planetary chemistry, biological metabolism, and geological cycles that has persisted for billions of years. When oxygen first surged into the atmosphere during the Great Oxidation Event, it nearly destroyed the biosphere by poisoning anaerobes and triggering a cascade of planetary freezes. But since then, despite massive extinctions and dramatic climate swings, oxygen has never again swung so wildly. Instead, it has been held within a narrow range, sometimes higher, sometimes lower, but always enough to keep complex life alive. To understand why, we must look at the quiet but powerful feedbacks built into Earth's system, mechanisms that act like invisible governors on a machine that could otherwise run off its rails. One of the most important of these stabilizers is the long-term carbon cycle, mediated by the weathering of rocks. When oxygen levels rise, organic matter burial also increases, because oxygen reacts with carbon. That burial sequesters carbon dioxide in sediments, lowering greenhouse gases and cooling the climate. Cooling slows weathering, which in turn reduces the supply of nutrients fueling photosynthesis. The result is a brake on further oxygen rise. Conversely, if oxygen levels fall, less organic carbon gets buried and more carbon dioxide builds up in the atmosphere. Warming accelerates weathering and boosts nutrient delivery, encouraging photosynthesis to pump oxygen back into the air. These negative feedbacks keep oxygen from running away in either direction. It is a delicate seesaw, mediated over millions of years by rivers dissolving rock, microbes fixing carbon, and sediments locking away the record. Another crucial player is volcanism. Volcanoes release reduced gases such as hydrogen and methane that can consume oxygen when they react in the atmosphere. In the Archean, when Earth was more volcanically active and the mantle still hotter, these reduced gases were abundant enough to keep oxygen levels suppressed for eons. After the Great Oxidation, volcanic outgassing declined, reducing this sink and allowing oxygen to stabilize at higher levels. But the system remains in balance. Even today, volcanic gases help prevent oxygen from rising far beyond the 21% we're accustomed to. If oxygen crept much higher, wildfires would become uncontrollable, igniting forests from lightning strikes and burning them to ash before ecosystems could recover. Geological sources of reduced gases act as a counterweight, keeping oxygen from becoming a universal accelerant. Phosphorus, the limiting nutrient of life, also governs the oxygen cycle. When continents are actively eroded, phosphorus washes into the oceans, fueling algal blooms and raising oxygen. When erosion slows, productivity wanes, oxygen production weakens, and levels fall. Over Earth's history, the dance between mountain building and erosion has repeatedly modulated oxygen levels. During supercontinent breakups, newly exposed rocks bled nutrients into the seas, while during times of tectonic quiet, the supply dwindled. The oxygen we breathe has always been linked to the restless drift of continents and the slow wearing down of mountain ranges. Burial of organic matter too plays its part. For every carbon atom buried in sediments, an oxygen atom is left free in the atmosphere. That simple stoichiometry underlies the rise of oxygen across deep time. When swamps in the Carboniferous buried immense quantities of plant matter, oxygen spiked to levels perhaps as high as 35% of the atmosphere, fueling dragonflies the size of hawks. When burial rates declined, oxygen fell back to safer levels. Earth has never allowed oxygen to remain indefinitely at its extremes, because the same processes that drive its rise, weathering, burial, nutrient delivery, always contain their own breaks. Even fire itself is a feedback. When oxygen levels climb too high, fire becomes more frequent, converting organic carbon back to carbon dioxide and limiting the burial that feeds oxygen accumulation. In this way, lightning and flame are not just destructive forces but planetary regulators. Forests that burn return nutrients to soils, limit excess organic buildup, and help keep oxygen in check. It is a reminder that what seems catastrophic at human scale can be stabilizing over geological time. The end result is not perfect stability but oscillations within a band. Oxygen has risen, fallen, and risen again across eras, but it has never vanished since the Great Oxidation, nor has it exceeded levels that would sterilize the land in perpetual fire. Earth's system, for reasons we only partially grasp, contains a set of linked processes that resist runaway extremes. We know this not because we have all the answers, but because we see the fingerprints in rocks, isotopes, and fossils. We read the story backward and marvel at its improbability. The haunting question is whether this balance is inevitable or contingent. On another world, with different volcanoes or less phosphorus, would oxygen have spiraled out of control? Was Earth uniquely lucky in finding this balance, or do planetary systems naturally fall into such feedback loops? We cannot yet answer. What we can say is that the breath in our lungs is not just the product of photosynthesis today, but of billions of years of give and take between air, rock, water, and life. Oxygen is not a free gift. It is a negotiation that has never stopped. If we listen closely, there are still more quiet guardians of oxygen hidden in Earth's cycles. One of them lies beneath our feet, in the realm of soils. When plants colonized land in the Paleozoic, they began drawing down carbon dioxide through photosynthesis and stabilizing soils with roots. Those roots accelerated the weathering of rocks, releasing nutrients and pulling more carbon into sediments. But soils also became active regulators themselves, storing organic matter for centuries or millennia before releasing it again. This intermediate timescale helps buffer oxygen production against short-lived swings. Instead of every autumn's leaf litter oxidizing instantly, some portion is stored, slowing the system's reaction and keeping the atmosphere from seesawing wildly. Another overlooked stabilizer is the ocean's biological pump. Tiny plankton photosynthesize near the surface, die, and sink, carrying carbon to the deep ocean. This not only sustains marine food webs, but also determines how much oxygen remains in surface waters. If the pump weakens, more organic matter decays in shallow water, consuming oxygen and lowering levels. If the pump strengthens, more carbon is buried in sediments, leaving oxygen free. Across geological time, shifts in the biological pump, triggered by nutrient availability or evolutionary innovations like silica-shelled plankton, have acted as another hidden lever on oxygen. These are not mechanisms anyone designed, but emergent properties of how carbon cycles through life and death. The ozone layer, too, deserves mention as a stabilizer of sorts. Once oxygen accumulated beyond a threshold, it began forming ozone high in the stratosphere. That thin veil shielded Earth's surface from lethal ultraviolet radiation, allowing more photosynthetic organisms to colonize land and shallow waters. In doing so, it created a positive feedback. More oxygen supported more life on land, which in turn produced more oxygen. Without the ozone shield, oxygen might have remained a tenuous phenomenon, repeatedly destroyed by radiation before stabilizing. In a sense, the ozone layer is oxygen's own bodyguard, protecting the molecule that built it. We also cannot ignore mass extinctions themselves. Each extinction event, while devastating for biodiversity, often reshaped the balance of oxygen. The rise of vascular plants, the fall of giant coal swamps, the dominance of different plankton groups, all of these restructured how carbon and oxygen were cycled. Oxygen levels never remain static because life is not static. The very organisms that depend on oxygen also co-engineer its abundance, sometimes pushing it up, sometimes pulling it down. We inherit a planet where oxygen has been sculpted not by a single feedback, but by countless overlapping loops. Perhaps the most humbling lesson is that no single stabilizer is strong enough alone. The weathering of mountains, the burial of swamps, the rumbling of volcanoes, the sinking of plankton, the crackle of fire, all play their part. Oxygen has remained in the breathable zone not because Earth found a permanent equilibrium, but because whenever one feedback faltered, others took up the slack. The planet, in its messy, interlocking way, stitched together resilience from fragility. That resilience is why we can breathe tonight. What would it mean if breathing itself is only possible because 1% of life survived? The Great Oxidation Event was not just a planetary chemical shift. It was a filter so severe that nearly every form of life known at the time disappeared. Anaerobic microbes, the architects of Earth's early ecosystems, found themselves drowned in the very oxygen that a few newly evolved organisms had learned to produce. Some escaped to niches underground, in the guts of sediments, or inside hydrothermal cracks. Others simply vanished. In that moment, survival was not about thriving or mastering the environment. It was about enduring in whatever dark or shielded space remained, holding on until the planet calmed enough to allow continuity. The oxygen we inhale today is thus a legacy of that knife's edge. It was not inevitable. Had oxygen risen too fast, or had the glaciations lasted a little longer, the surviving 1% could have been none%. Had the few photosynthetic pioneers collapsed under their own weight, Earth might still be a microbial world wrapped in methane haze, unknown and unknowable to us. Every breath we take contains this irony, that oxygen was once a deadly toxin, and only by catastrophe was it transformed into a gift. The paradox of oxygen is also a lesson in fragility. It teaches us that survival is often not about dominance, but about finding hidden corners and waiting through instability. Life's resilience lies not in strength alone, but in its ability to retreat, persist, and re-emerge. The microbes that weathered the Great Oxidation did not foresee the future. They were not heroic. They simply endured long enough to pass on their chemistry, and from that chemistry came all of us. To view oxygen as both poison and sustenance is to understand the double edge of existence itself. The same molecule that powered the rise of animals nearly ended the possibility of animals altogether. The same process that froze the planet also laid the foundations for more stable climates to come. This is the strange comfort of deep time. Catastrophe and renewal are never fully separable. They are the same motion, seen from different vantage points. For sleepless sapiens spiralling at night, this story may sound uncomfortably close to our own. We breathe without thinking, but every breath is a reminder of improbable continuity. The fact that you can inhale calmly at this moment is because countless generations of organisms endured poison, starvation, and ice. Their survival carved out the atmosphere that now rocks you to sleep. It is a reminder that fragility and resilience are not opposites. They are partners. Life is fragile precisely because it can be resilient, able to fold itself into corners until the storm passes. Perhaps the haunting question is whether this pattern, near loss, followed by improbable recovery, is universal. If we looked to other worlds and found oxygen in their skies, would we also find histories of almost total extinction, with survival measured in single digits? Or is our story a one-off, a fragile miracle strung between collapse and renewal? We cannot yet know. What we can know is that our existence is balanced on the breath of survivors we will never meet, microbes whose only legacy is the air itself. It is worth pausing to imagine what that survival looked like. Not grand, not triumphant, but modest, almost invisible. Picture a world of ice and rust, where vast oceans were locked beneath frozen crusts, and the air itself was strange and unstable. Somewhere, in cracks along a volcanic ridge, or in layers of mud where sunlight never reached, tiny colonies of microbes kept dividing. They were not thriving in the sense we like to imagine, but simply continuing, cell after cell, a fragile rhythm against impossible odds. Their persistence stitched a thin thread of continuity across a planetary disaster. Without them, Earth would have reset, and there would be no complex life to wonder about its own origins. That 1% of survivors is a sobering scale to think about. We often speak of mass extinctions in terms of what was lost, but rarely in terms of what was preserved. Here, in the first great biological crisis, preservation meant almost nothing compared to loss. 99% of lineages were gone forever, erased from the possibility of futures. Yet that faint remnant carried forward the genetic and metabolic potential that would eventually fuel oxygen respiration, multicellularity, and eventually animals. The fact that you are alive today is evidence that enough of them endured, though barely. There is an existential quiet in realizing that survival does not always look like progress. In deep time, it is often indistinguishable from waiting out the poison, waiting out the ice, waiting out the geochemical chaos of a young planet. That patience, if one can even call it that in the language of microbes, is what seeded the possibility of everything else. Without it, even oxygen itself would have been only a temporary anomaly, a chemical spike destined to collapse into silence. Seen this way, breathing becomes less an act of consumption and more an act of inheritance. Each inhalation links us to those ancient survivors who clung to niches through the Great Oxidation Event. Their chemistry became our chemistry. Their endurance became the reason air is breathable. To recognize this is to recognize that our lives are built on the edge of fragility. We are not guaranteed permanence, any more than they were, yet the continuity they gave us suggests that even in near-total collapse some thread remains. That thread is what binds us to the story of Earth itself. And perhaps that is the comfort hidden in catastrophe. The reminder that survival is rarely universal, but it does not have to be. It only takes a fraction of life to hold the torch through darkness, long enough to pass it on. Oxygen is the monument to that persistence. Tonight, as you drift into sleep or move through your day, every breath is a whisper from that 1%. A reminder that existence is fragile, yes, but also remarkably hard to extinguish. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.